Welcome everyone. It's 2:30 here in Barcelona, and for a lot of you actually it's early in the morning. I would like to kick off the Exposome Data Challenge Event. It's the first time we organize such type of events, but we're very excited and we got a lot of answers from all around the world, registration and also abstracts submitted. I would like to introduce the team who worked on this event, the committee, with Xavier Basagagna, Juan Ramon Gonzalez, Charline Warembourg, Paula Petron, and Mark Shadow Ian. We are a mix of exposome researcher, biostatistician, bioinformatics. And also I want to thank for project management, Rodney, and communication, Yvette and Aleix, who made this event possible. You must have received a lot of emails from them already. I wanted just to tell you who actually is going to attend this event. We got people from all around the world, a lot from North America and Europe, but also some people from the rest of the world, from South America, some from Iran, from Asia. So we're very happy about this. And just to remind you, the objective of this meeting, our idea was to promote innovation in how we can analyze exposome data, but coming from different fields. We have people coming from more epidemiology, bioinformatics, omics world, but also data science. So I hope you will find it useful and we can learn from each other. And the main objective is for us to collaborate and brainstorm on these new ideas. For this event, over these 3 days, we're going to have 25 presentations. Some are individual, some are teams who worked on these challenges. And we had actually 39 abstracts sent. Everyone had access to the same data set, which was a mix of exposure, of omics data, covariates, and 6 main health outcomes. The presentation after me from Martine will explain more where this data come from. We had a mix of challenges on how to combine this exposure, how to integrate omics data, but also how to extract causality from this exposome data. And this is how we divided the sessions over the 3 days. This is important. This event is okay, it's for collaboration and brainstorming, but also we want to award the best team who worked on these challenges. And we invite everyone to vote. We're going to have one best presentation selected by the general audience. So we invite you to vote. We'll put in the chat the link to vote for each topic. And we're going to have one selected by the committee. We don't have specific criteria for the best presentation. We thought on clarity, novelty, and relevance for our challenges. Don't miss the networking time. It's going to be at 4:45 or 10:45 for Eastern time. We're using this platform called the Spatial Chat. So if you click on the link we sent you in the email, it's also here in this presentation. You're going to land in this lounge place where you can find your peers. You will have it. Please put your camera and your mic on, and you can actually move around in different tables, speaking with your peers. And we also have rooms for a different topic. One will be where Martine will be, and if you want to have more questions, speak with her about her presentation coming up, or the 2 other topics. So you can move around from the main lounge to the other rooms. And that's it for the introduction. Please let us know if you have any question. Use the chat, and I give the floor to Martine.
Hi everyone. I hope I'm sharing my screen now. I hope you can all see this.
Yes,
yeah,
we can see your screen.
Good. So thank you all for joining this event. It's very exciting to see so many people interested in this data challenge. I want to thank Léa especially for the enormous work that's gone into organizing this, and of course the rest of the committee as well. So in this first lecture, we thought to present an overview of HELIX, of the project, and of some of the first findings and first lessons, that have really led to the challenges that we're going to be looking at in the coming days. So I will start straight away with the project. This was a project that was funded by the Framework 7 project program of the European Union. It started in 2013, so quite a few years ago now. And at that time point, our aim was to provide our general aim was to provide wide coverage of the exposome, of different domains of the exposome, and to evaluate its effects and impact during early life. So we really focused on the early life time periods because it is a period of very vulnerable, rapidly developing organs, and it has any effects at that early time point can have lifetime consequences. So we took that as an important starting point for building the exposome. We did that by basing our study in 6 existing European birth cohorts. So these were all birth cohorts that were already ongoing. They started at a similar time point. They each already had some data related to environmental exposures. And altogether, there were around 30,000 mother-child pairs in these studies, for which we already had a set of existing data. And in this large population, we characterized the urban exposome through geospatial methods. And then from that larger population, we selected a sub-cohort of 1,300 mothers and children, mother-child pairs, where we did all the intensive work. So there we did a new follow-up in the 6 cohorts of these 1,300 children with common protocols to collect biosamples, to measure biomarkers, to do the omics analysis, and these children were assessed through clinical examinations. And then nested within that, we had some more detailed panel studies that were really aimed at looking in more detail at personal exposures and variability of exposures. So these are the exposures that we measured during pregnancy and in childhood. The children were around 6 to 11 years old when we did the assessments. We characterized the urban environment, as I said, with a number of exposures, including outdoor air pollutants, noise, traffic noise, also traffic load and density, some characteristics of the built environment, green spaces, UV radiation, and some meteorological variables. And then this was done through GIS methods, geospatial modeling. Then in the more individual environment and the chemical environment, we used biomonitoring methods to measure concentrations of chemical pollutants in the blood and in the urine of the mothers and the children, including persistent organic pollutants, organophosphate pesticides, phthalate metabolites, a selection of phenols, metals. And then we had questionnaires to get information on tobacco smoke exposure. We built prediction models on indoor air pollution. And we had questionnaires on lifestyle exposures, including diet, physical activity, sleep, and a list of social factors. So that gave us about around 100 exposures at each time point, 100 in pregnancy and 100 during in childhood. We then, in the same study population, so again, when the children were 6 to 11 years old, the biosamples collected at that time point, we used a range of platforms to measure the internal exposome, as we call it, through both sort of more non-targeted assays, arrays for methylation, for DNA methylation, for expression, and then some more targeted assays to measure proteins and metabolites. So these are much more targeted proteomics and metabolomics platforms that we used. Also, mainly because at that time in 2013, these were the best available techniques to do that, that fitted within the resources of the project. So this was done in all 1,300 children that participated in the sub-cohort. And then in those same children, at the same time point, we measured health outcomes, including neurodevelopment through measures of cognition and behavior. We had anthropometric measurements. We measured bioimpedance, for example, blood pressure. And we had an assessment of respiratory health through questionnaires, as well as through lung function testing, spirometry. And this was done through standardized common protocols and questionnaires in each of those 6 cohorts. So we really tried to standardize all the assessments. And the research questions that the main research questions we were aiming to answer related to 3 main areas. The first one was more on describing and characterizing the early life exposome. So to describe its correlations, its determinants, the variability in these measurements. The second part related more to the integration of the internal exposome. So can we identify molecular omics signatures associated with multiple exposures? And then the last part, we then tried to link the exposome or these multiple exposures to child health. And with this main question is for us was which are the early life exposures or exposure patterns that are most strongly associated with child health outcomes. So to show you some results and some messages, some first findings, some conclusions. First of all, on the descriptive part, we started by building a correlation matrix. And this is the network visualization of that correlation matrix, showing the correlations between all the exposures. And this figure is for the childhood time point. What we concluded from this, there are strong correlations between exposures within groups, and these correlations are much higher than the correlations between groups. So the different groups are much further removed from each other than the points within the groups, which maybe as you expect. We also see quite a lot of connections still between groups, for individual pairs of exposures. And then, of course, we see some clusters, especially here in the outdoor or in the urban exposome, where all the exposures are close together and quite highly correlated. So this gives us some initial information on the structure of our exposome. The next question then is, can we actually reduce the dimensions of this exposome? Can we summarize these exposures into a smaller number of variables? And that proved to be very difficult, at least when we take all those exposures together. It was not easy, for example, with this principal component analysis, to reduce the dimensions of this exposure picture into a few exposure scores. For example, to explain 87 variables in the pregnancy exposome, we would need 65 principal components to explain 95% of the total variance. So we weren't able to build good principal components when we take all these exposures together. It gets somewhat easier when you focus on certain parts of the exposome. So if you do this within the urban exposome, it works better. If you do it within the chemical exposome, it works somewhat better. A next important part of the study, or at least what we did with these panel studies, was to look at variability in the different domains of the exposome. So we had different parts of the study that looked at variability in the urban exposures, in the chemical exposures, but also in the omics layers. And this is described in a series of papers. I won't go into the details now, but for example, we see, and this is obviously well known, but it is important to characterize that in these type of studies, that for the non-persistent chemical pollutants, for example, there is indeed a lot of day-to-day variability. And this is important information to then take into account in the interpretation of the studies linking the exposome to health, and even eventually in terms of correcting or adjusting for the errors in the measurement. This is a new work that we haven't published yet. This is submitted, where we looked at the variability in each of the omics layers. So each of the 6 layers, we try to characterize the intra and inter-individual variability, as well as the cohort between cohort variability in these omics profiles. And this was done with the measurements that we had 6 months apart in the 156 children that participated in the panel studies. And here you can see the pictures with the percentage of the variance explained by each of these components. There is the main conclusion is that there's a lot of heterogeneity between the features. So some features, some metabolites are highly variable, others much less so. And this we see in each of these layers. Overall, DNA methylation is the most stable of the layers. So there we have a higher percentage of features that has a low inter-individual variability, whereas the gene expression layer has many more features, a higher percentage of features with a large intra-individual variability. And the other layers, so the proteins, the metabolites, that's somewhat in between, as I said, with a large heterogeneity within these layers, within features from the same layers. So then moving on to the integration of the molecular signatures. This is work that hasn't been published yet, but has been submitted for publication. Here we try to associate each of the exposures in our data set with each of the omics layers. Again, I won't have time to go into the details, but this is a network of the associations that we found in that study, and where we try to build clusters of how these features go together. And we find certain clusters related, for example, to chemicals and diet variables, clustering together with certain omics features. Over the whole, we can say that the prenatal exposures predominantly related to the CpG feature, so the DNA methylation, and much less to the other omics layers. Whereas in the for the childhood exposures, we see a picture that's much more spread out over the different omics layers. We're also working on studies that look at much more specifically at specific exposure groups. So here's a publication on the left on multi-omics signatures related to tobacco smoking, looking both at maternal smoking and childhood secondhand smoking. And again, we see for especially DNA methylation signatures related to maternal smoking, showing persistent and dose-dependent changes in the methylome. And then for childhood tobacco exposure, that is secondhand smoke exposure, we found certain metabolites and protein markers that potentially indicate early biological effect. Another good example is a paper that was published last year in hepatology, where we used this database to look at perfluorinated substances and their association with liver enzymes in children. And we used the metabolomics layer to get some information on possible early responses to these exposures that were also related to the outcome, so to the liver enzymes. And we found that the PFAS exposure was associated with alterations in some key amino acid and phospholipid pathways that were also characterizing liver injury. So a few brief conclusions regarding the omics integration. The molecular signatures that we found may represent markers of exposure or exposure sources. So on the one hand, we have some that indicate more the sources of exposures, and others that may indicate more early signs of response to or damage from environmental agents. So there we might be looking at early preclinical changes in the biological pathways. But these are very early studies. There's a lot of work ongoing on this database, but also obviously these results require replication in larger populations, in vitro studies. They also require prospective follow-up because our data was at one time point, at least for the health outcomes and the omics layers. And then it's also important, given the findings we have on the variability in these omics signatures, repeated time points of measurements are important. Then moving to linking these multiple exposures to child health using a more exposome-wide approach than what has been done up to now. We have published a series of papers relating our exposures to the different health endpoints that were measured. Here's a list of the different papers. These papers all followed a fairly similar analysis plan. So I will give an example of one of these. And this is the paper that looked at childhood obesity. And as I said, the other papers followed a similar analysis plan where we started with an XWAS approach. So linking each of these exposures in a separate regression analysis to the outcome, but correcting for multiple testing. And in the results for BMI, we found only smoking related to the child's BMI, maternal smoking in the prenatal exposome. And then when we went to the childhood exposures, we found many more associations, some negatively associated with BMI, some positively associated with BMI. And then we went to a second step where we applied a variable selection approach. In this case, the DSA, which stands for deletion, substitution, addition algorithm, which is a variable selection method. So it goes through the different exposures to pick the set of exposures that best predicts the outcome. And we use that set of selected variables then to build a multiple exposure model. So in this model, these exposures are added together into the regression analysis. And this gives us a somewhat reduced set of variables compared to the XWAS analysis. But the conclusions are quite similar. So the similar groups of exposures are related to the outcome. So doing that, we systematically analyzed all these exposures related to a set of these different outcomes. And we get a picture of which exposures may be associated to these outcomes. And we also get a picture of some exposures that may be more specific to one outcome, others that may be more associated to outcomes across the board. I won't go into the details now. This is for the exposures during pregnancy, where, for example, tobacco smoke comes up in quite a few different outcomes, whereas some of the chemical exposures, for example, phthalates or perfluorinated compounds, are only seen to be associated with one of the outcomes we studied. And similarly for the exposures that were measured during childhood. So there's an interesting picture emerging in terms of associations between the exposome and child health using these exposome-wide approaches. So what are some of the advantages of doing an exposome-wide study instead of a more traditional one exposure, one outcome approach? Well, first of all, as I said, it gives us a more systematic and comprehensive analysis whereby we can screen for many suspected risk factors. This approach corrects for multiple testing, whereas if you did the same cohort study, but you published each of these groups of exposures in a separate paper, you would not correct for multiple testing, even though this would still be, you would still have the same issue. So this could be an advantage of an exposome-wide approach. We avoid publication bias by publishing all associations. So even those that normally would not have been published because they were negative or people didn't even look at them, this is all published systematically in these papers. We correct for confounding by co-exposures. So these multiple exposure models can actually account for for possible confounding. And there is an element of suspect screening. So we look at many risk factors that have maybe not previously been associated to that particular outcome beforehand. And this may be a way to detect novel risk factors. Ultimately, this approach may be useful for priority setting. So it might be a way where we can intervene on agents that are most likely to be associated with health. But it's obviously a first screening analysis and needs follow-up in much more targeted studies. There's obviously a lot of challenges and limitations to this way of analyzing data. First of all, comparisons of exposures, so actually comparing or ranking exposures is still very limited, and we have to be very cautious with that, especially because these exposures are all measured with a different measurement error, different types of measurement errors and different magnitude of measurement error. An example is the non-persistent chemical pollutants, where we know that by measuring these in one spot urine, we have a large measurement error, which could have given us false negatives. In the future, obviously, improving the accuracy of each exposure assessment is important. We're working on that in our follow-up studies. Error correction models might be a way to try and start getting more comparable data for these exposures. And I refer to this paper that's just been published on how we may use repeated biospecimens, but also error corrections to reduce the effects of these type of errors. Then we know we may have false positives in these studies due to the high correlations between the exposures. And this may occur predominantly within exposure groups, but we may also have problems between exposure groups. We did methodological work based on simulation studies at the beginning of HELIX that showed us that some of the analysis methods, especially the XPOS, have quite a high level of false positive, quite high false positive rate. So we are concerned about that. And this is why it's important to have complementary analysis strategies, but also to try and integrate in future studies more a priori knowledge about which exposures may be associated, and also to work on replication studies in different settings.
Martine, yeah, if you can wrap it up.
Sure, I have one more slide. So. Okay. reverse causality in HELIX is an issue because during childhood we measured exposures, omics, and health outcomes at the same time. And I'm happy to say that we are now implementing a prospective follow-up of the same cohort to get longitudinal data. Power and sample size are an issue when we do so many different comparisons, and we see that in some of our papers, really the sample size wasn't enough to get strong associations. Here it's important to think about enlarging the sample size, but also to find ways to reduce the dimensions in this exposure picture so that we look at less variables. Residual confounding is remaining a problem, just like in other traditional epidemiological studies. And here, obviously, more targeted studies, but also replication and triangulation of evidence is important. And then there are plenty of issues that we have not yet tackled in this first series of papers. And these include interactions, looking at combined exposures and mixtures, looking at the further complexities in this data in terms of causal structures, data hierarchies, and also the hierarchy between the exposures, and also integrating repeat measurements, so longitudinal exposome data. These are all issues that have not been tackled yet. In the examples I showed you, we haven't tackled any cross-omics integration. And in HELIX, also because it's a study that started quite some years ago, we did not apply yet sort of the new techniques to measure unknown or emerging exposures. And here I'm specifically thinking about the high resolution mass spectrometry methods that are now being developed to get much more, to measure many more molecular features also related to the unknown part of the chemical exposome specifically. So it is still early days and we have many challenges ahead of us. And I just want to finish by saying that I'm happy to say that in the athlete project, which is kind of a follow-up to HELIX, we have set our aims to start working on some of these challenges and to really make progress on advancing on those points. And this event today connects to that really well. And I'm really excited to see the contributions. And yeah, I hope you will enjoy the next 3 days during this event. And I want to stop here and just acknowledge everybody who worked on HELIX, because this is a very large effort with many collaborators from different institutes across Europe. I will stop there.
Thank you, Martine. That was a very good introduction. If there are any questions, please put it to the chat and Martine can answer writing. And you can also have a chance during the break to go to the room with Martine's special chat. We're moving on now to the first topic about analyzing the effect of mixture exposure with the chair Charline Warembourg, who did a postdoc at ISGlobal and recently moved to Inserm in Rennes. The floor is yours, Charline.
Thank you, Léa, and good morning or good afternoon, everyone. So I'm pleased to share the session on exposure mixture. So today we have 6 speakers, and unintentionally all coming from North America. And each speaker will have around 12 minutes to present their methods and results, followed by 2 to 3 minutes of discussion and comments after each presentation. And I will let you know, so to the speakers, I will let you know when you will have only 2 minutes left to finish your presentation. And I encourage the audience to put their question and comment in the chat. And at the end of the session, we will have 50 minutes of general discussion. So thank you to the speakers and to all of you for joining this session. And I hope you will enjoy it. So now let me introduce our first speaker, Glen McGee from the University of Waterloo in Canada, who will talk about quantifying exposome-Health association with Bayesian multiple index models. So Glen, the floor is yours.
Sure, thanks. Great, so I'm Glen McGee. I'm going to present some joint work with Andra Wilson, Brent Kuhl, and Tom Webster. And as you say, I'm going to be talking about Bayesian multiple index models. So our Bayesian multiple index modeling approach combines the strengths of two popular mixture methods. Linear index models, examples of which include weighted Quantile sum regression and Quantile G computation, as well as response surface methods like Bayesian kernel machine regression, or BKMR. I'll just briefly highlight what these are. So linear index models are essentially linear models like this, where we're regressing an outcome Y on various or P different exposures. They're often quantized, meaning they're turned into, say, deciles coded as 0 to 9, and further adjusted for some covariates Z. But the main idea is you fit a linear model like this, and then you decompose the coefficients of the linear model into two pieces. One, quantifying the overall mixture effect, so the effect on the outcome of increasing all exposures, say, by 1 decile. As well as these component weights, BP. So the appeal of these approaches are that they're really interpretable. These BP weights indicate the relative contribution of each component to the overall mixture. However, they're a little bit restrictive. They assume linearity, often on the quantile scale, and they assume no interactions between any exposures. And I've just highlighted there's a couple different ways of doing this. On the other hand, something like Bayesian kernel machine regression, we take P different continuous exposures and we fit a model that looks like this. So we're again adjusting for several covariates Z. And the main idea is that we're estimating some P-dimensional unknown exposure response surface H. So H is a function of your P individual exposures. And we specify it non-parametrically. And the advantage is that this allows for nonlinear exposure response curves, and it allows for higher order interactions among the different exposures. And so this is really flexible. How do we go about interpreting results? Typically, we'll estimate exposure response curves. So we'll vary some exposure along a grid of values, holding everything else constant, and then we'll estimate that exposure response surface. And so we can do this for all P different exposures, holding everything else constant. We could also look at, say, two-way interactions by varying an exposure along a grid and holding another exposure at, say, the 10th percentile, and then doing the same thing, holding another exposure at the 90th and comparing those curves. And so typical results of this type of analysis might look like this. So this is just an example of an analysis with 18 different exposures. So on the left, we get 18 different exposure response curve estimates. And so you can scan through all of these and characterize the association between an exposure and the outcome, holding everything else constant. On the right hand is how you typically consider two-way interactions. We're plotting exposure response curves, holding another exposure at the 10th, 50th, and 90th percentile. And as you can see, even with 18 different exposures here, this becomes pretty difficult. There's hundreds of plots here to scan through. So you can imagine if you had, say, 100 exposures, this would be a lot more difficult. So there's a fundamental trade-off between these two classes of methods. Linear index methods are really easy to interpret, but they're somewhat restrictive. Whereas BKMR, being very flexible, is difficult to interpret when there's a lot of exposures. And so our proposed approach is trying to balance the strengths of both of these. So the Bayesian multiple index model, we're first going to partition our P different exposures into M mutually exclusive groups. And then we're going to construct our model as follows. So it looks just like the BKMR model. We're still adjusting for some covariate Z. And we have this unknown function we're estimating H. But now H is a function of M different indices. And by an index, I just mean a weighted sum of different exposures, much like in a linear index method. So the advantage is this is going to allow each index to have a nonlinear exposure response curve, and it's going to allow interactions among different indices. However, it does make a couple assumptions. One is that the response curves for exposures within a single index take the same shape. They can be flatter or stretched, but they all have roughly the same shape. And further, we assume that exposures within the same index, within the same groups, do not interact. So just for some intuition about this, BKMR, we have to estimate a P-dimensional exposure response function H. So H takes as inputs all of our P different exposures. So you could have 100 different exposures, 100-dimensional surface. Bayesian multiple index models reducing the dimensionality by collapsing exposures into indices. So now we're estimating an M-dimensional function H which takes as inputs these m different indices. And so this reduction of the dimensionality helps with interpretation as well as prediction accuracy when the assumptions are met. Right, so how do we interpret results from this kind of a model? Well, typically, much like BKMR, we'll estimate response curves, but now we can do them at the index level. So here we could just plot m different index-wise response curves rather than p exposure-wise response curves. Similarly, we could look at two-way interactions among different indices. And then we could quantify the contribution of exposures to each index by looking at the actual index weights theta. So theta ml will quantify the contribution of the ELF component to the mth index. And for identifiability, we have a couple of constraints on these, which I won't dwell on. So how does this actually do in the exposome data? So we're applying it to the outcome of interest for us, which will be a BMI z-score. So it's a standardized BMI. So we're including in our H function, or including into our consideration, 150 continuous exposures. So we're restricting attention to the continuous exposures. We're excluding the categorical ones. And we're grouping them a priori into 29 indices, which correspond to the predetermined domains or families. So for example, organochlorines and metals are different indices. Further, we're splitting indices by pregnancy and postnatal measurement. So we have an organochlorines during pregnancy index, and then we have an organochlorines postnatal index. Because we have so many exposures here, we're also implementing some Bayesian variable selection to apply some shrinkage. Further, we're adjusting for several covariates like cohort, gestational age at birth, and several others. So the first thing I want to point out are index-wise posterior inclusion probabilities. So these give us a sense of how often an index is being selected into the model. And so for the vast majority of our indices here, the index-wise posterior inclusion probability is less than 50%. And so we're just going to focus on these four indices with the strongest signal here, which are organochlorines, metals, and built environment, all measured postnatally. And then water DBPs during pregnancy. And so here we're estimating index-wise response curves for these four indices of interest. And so for built environment, there's not too much exciting going on. It's a pretty small effect seeming. For metals postnatally and water DBPs pregnancy, there seems to be somewhat of a linear association. For metals, a positive linear association. For water DBPs, a slightly negative association. But the really interesting one here is organochlorines, which has a pretty strong nonlinear effect. So as organochlorines increase towards the median, there's a very strong negatively linear effect on BMI, and then it starts to level out in this sort of hockey stick shaped curve here. So that's at the index level, but what if we want to know how each of the exposures contribute to these indices? We can also look at posterior inclusion probabilities for the individual exposures themselves. So we're just highlighting these four components of these four indices here. And for built environments, there's nothing that really is standing out. However, for metals, I think these are copper and cesium, have the strongest posterior inclusion probabilities. So these seem to be driving that index in part. Organochlorines, there are three components that are really standing out: PCB 170, HCB, and DDE, which all have posterior inclusion probabilities near 100%. So these are almost always selected into the model. Posterior inclusion probabilities give us a good sense of variable importance or maybe the signal, but it doesn't give us a sense of effect size. So we can further look at the posterior distribution for the actual index weights, the actual weights theta. And much as before with built environment, it's pretty hard to pick out the effects of each of these, and that's largely because the overall effect of that index is pretty weak. For metals, however, copper and cesium we see seem to dominate this index, but it's kind of hard to pick apart which one is contributing more, hence the really wide credible intervals here. With organochlorines, the story is a little bit different. HCB seems to have the strongest effect on this index. It has by far the largest weight and pretty tight credible interval around it. Most of the other components are shrunk to zero. However, PCB 170 and DDE are still contributing to this index with a positive weight and pretty tight intervals around them. So they're not being shrunk all the way to zero. So we're able to pick up on some weaker effects, even though they're not dominating this whole index. And so with that in mind, we're going to focus a little bit further on these three exposures and look at the component-wise, or just exposure response curves, much like we could with BKMR. And as I said, these should all have the same shape. They're just flatter or stretched, depending. And these look very much like the index-wise curves. One thing I should point out is that there's quite a lot of uncertainty around these, and that's essentially because we're plotting something analogous to fitted values in simple linear regression. Alternatively, you just might be interested in inference for, say, a slope. So we could do something similar and look at component-wise contrasts. So what I'm plotting in the middle here is comparing HCB at, say, the 75th percentile, comparing to the median. What would be the estimated mean difference in the outcome as a result of that change? And so we see these strong nonlinear effects. And for DDE and PCB170, we see strong negative effects as well. So with larger exposures to DDE, HCB, and PCB170, we expect BMI to be lower. So that's basically the story in the univariate analyses. But we can do a little bit better. We can look at interactions among these indices. So here what we're doing is we're plotting the same. Sure. Here what we're doing is we're plotting our index-wise response curves for, say, water DBPs during pregnancy, setting built environment to the 10th, 50th, and 90th percentile. And if the slope of these or the shape of these differs across these different percentiles, that would suggest some interaction among these indices. So overall, there's not too much evidence of interaction except between water DBPs and organic chlorines. So when organic chlorines are at the 10th percentile, we have a negative linear association with water DBPs. And then when organic chlorines are at their 90th percentile, we have basically a null, maybe slightly positive linear association. So there's a little bit of evidence of interaction here, but not terribly strong. Because I'm limited in time, I'll just jump to some limitations here. So as I said, we're making several assumptions. One is that the response curves for exposures within the same index take the same shape. They can be flat or a stretch, but they have the same shape. We're also assuming no interaction among exposures within the same index. So two different metals can't interact, but metals and organic chlorines altogether can't interact. We're applying variable selection, which could conceal some small but non-null effects. Thankfully, in organic chlorines with that strong effect, we're still able to pull out some weak non-null effects, though. And one other limiting factor is computing time, because the MCMC we're doing requires inverting pretty large matrices. And just before I finish, I'll just summarize here. The Bayesian multi-index model is really a framework that represents a spectrum of models that vary in flexibility and interpretability depending on how you construct your indices. So the most restrictive case, you could use a single index model or a linear index model as a special case. And at the other end of the spectrum, you could have BKMR as a special case. So both these different classes of models are included in this more general framework. And it also allows for a lot of other useful structures along that spectrum. Like you could look at interactions between a multi-pollutant index and individual covariates if you were to include something directly in that non-parametric function. But we didn't have time to do that here. And just a couple extensions that might be useful. We can also impose constraints on the index weights, much like weighted quantile sum regression, which I'm sure we'll hear about a little bit later. If you have some prior knowledge that exposures act in the same direction, we can impose that constraint here as well. And moreover, if we have exposures that are time varying at a pretty high resolution, we can also implement a distributed lag structure within the same general framework. So with that, thanks very much for your attention. Let me know if you have any questions, and feel free to reach out via email afterwards. Thanks very much.
Thank you very much, Glen. It was very interesting, and this method seemed very, very promising. So if anyone have a question, you can put it on the chat. I saw that Léa has a question, and she's wondering if these models can deal with categorical exposures.
So no, so it's built mainly for continuous exposures. It's essentially smoothing over a surface. That's definitely one extension we want to think about, how we would consider interactions with a categorical covariate. Right now, you can sort of stratify based on different levels of the covariate, but you lose a lot of power doing that, I think. So the short answer is no, but maybe in the future.
Okay, thank you. And we have another question. How can we check no interaction within the same index group of exposures?
How can we check that? Yeah, so that's an assumption of this approach. You could do something like a targeted analysis. So you might fit like the full BKMR, but just on the exposures within a single index, right? So if you want to check within organic chlorines, maybe you fit a model just to organic chlorines and fit the full BKMR and see if those components interact, just to give you a sense of security about that assumption. That would be one approach. And
another question, is there anything to gain by removing variable with low posterior probability and refitting a new model?
Sorry, could you ask that again?
Yeah, sorry, the the chat is moving, you receive a lot of questions, so I cannot read the end of the question. I think the question was if there is any gain to refit a model restricted to only the exposure with high posterior probability.
Oh, I see. Maybe a little, but honestly, the variable selection itself is taking care of most of that. So most of the variables that aren't contributing a lot are getting shrunk all the way to 0. So I don't think you would gain much by refitting it. It's possible you would, reduce the uncertainty a little bit, but I wouldn't recommend that approach.
Maybe only one more question, and we can keep the other for the discussion. So does your method allows repeated measurement of the outcome?
Yeah, so we haven't actually tried this on longitudinal outcomes. It is set up for correlated outcomes, so you could incorporate a random intercept, but that's a pretty simple longitudinal model. You, in principle, could allow for longitudinal data, allowing random slopes or something like that, because it's based around a mixed effects framework, but that's not something we've actually tried out yet.
Okay, thank you very much. And I will keep the other question for the general discussion. Great. So now I'm pleased to introduce Vishal Midya from the Icahn School of Medicine at Mount Sinai, who will talk about novel penalized LASSO type Bayesian weighted quantile sum regression approach for highly correlated multi-group mixture analysis. So Vishal, the floor is yours.
Can you hear me?
Yeah.
All right. Can you see my screen also, I guess?
Yeah.
All right. Hi. This is a LASSO type Bayesian weighted quantile sum regression framework for highly correlated mixture groups. This work has been done with Dania Valvi and Elena Colcino, both who were at Mount Sinai. Some background before I go into the main framework. Weighted quantile sum regressions have been there. It's very popular and to model exposure mixtures. The basic philosophy here is you have individual concentrations of single exposures, which might be very small below the level. But once you do a cumulative exposure, it might be substantially high, or it might have some relation to the health endpoints. Well, quite recently, there have been some Bayesian counterparts of these weighted quantile sum regressions, which was proposed. One was proposed by Elena Colcino into 2020, which is called the Bayesian weighted quantile sum, BWQS. Which enjoys the flexibility and the stability of the usual Bayesian procedures. And then this year, by Wheeler et al., they also proposed a similar model, which is called the Bayesian group index regression. They're very similar in terms of the parameters. The priors are almost similar, but mathematically they might be a little different, but they're very nice and flexible models, which take care of this Bayesian version of WQS. Now, what's yet to be done? Now, these Bayesian methods, they're Bayesian hierarchical models, which are very much flexible, and it might lead to severe overfitting. Now, we do not have, since it might lead to severe overfitting, particularly for highly correlated exposures on multiple groups, it might be severely overfitted. Now, how do you address the problem of overfitting? Introduce the statistical regularization of the penalty terms. That's how people do it in usual linear regression framework. What's the motivation for this method? This is a correlation plot of all the chemical groups, perinatal chemical groups. And then you can actually see we have the metals, OC pesticides, PCBs, OP pesticides, phenols, phthalates, PFAS, and PBDs. Why I started working on these highly correlated exposures, because you can see these correlations between these PCBs, phenols, and phthalates, they're pretty much high, almost near 1 now. And then between these groups, group of chemicals, there are correlations, but they're relatively lower. So the idea was to, like, if I fit this in a Bayesian model, it will be highly overfitted. So how do I combat that? So we introduce our methods, and what's the novelty? Like, what's exactly what we are adding to this method here? We are adding some penalty term or the statistical regularization through a Bayesian LASSO type modeling. And a Bayesian lasso, there are different versions of Bayesian lasso. It's almost a branch of topic in Bayesian literature. And then in particular, we implemented Bayesian group lasso or elastic net to model the variances of each of these group mixtures. Because by modeling the variances, we can actually get the estimates. And then in some cases also, these different groups can be modeled to have correlations, or they might be modeled to have uncorrelated. For example, Bayesian fused lasso. So we're basically building a framework where you can have group lasso, fused lasso, elastic net, depending on the problem. All right, what's the mathematical innovation here? I'm not going to the equations, but the basic idea here is to model the Laplace distribution as a scale mixture of normal distribution and the exponential density. Now, this has been done by Icahn et al. In 2010, almost 10 years ago. I'm just implementing that basic idea right here. And I'm applying this idea of scale mixing to our Bayesian framework, Bayesian W weighted quantile sum framework. Okay, that's great. But does this method work in real life? Yes, it does. So we are testing this model, Bayesian group lasso method, addressing the aim. If our to evaluate the association between prenatal environmental chemical exposures and the childhood BMI. So we have the chemical environmental prenatal exposures and childhood BMI. That's what we are looking for here. Some conceptual framework using the directed acyclic graph. We want to model, this is our outcome, the blue one. We want to model the body mass index, and our exposures are almost 8 different chemical groups: OC pesticides, PCBs, OP pesticides, metals, PBDs, PFAS, phenols, and phthalates. We have almost like 40 chemicals right here. And our confounders here are maternal education cohort, 5-6 different cohort, parity, age, BMI, and fish intake. So these chemical exposures versus our outcome of BMI Z-score. What do we observe here? Just like the previous talk, we are seeing some, so we have different chemicals, so chemical groups, and we have our forest plot here, and we have the point estimates and the confidence intervals. We can see that PCBs, OC pesticides, and the metals, they are significant. It's not significant in terms of Bayesian significant, but it's significant because it is not contained in this. The estimate does not include the 0. Both metals and OC pesticides, the organochloric pesticides, they have some positive association with the BMI Z scores, and PCB has a negative association. And if you go to the right side, we actually plotted these estimated weights or the posterior probabilities, estimated weights here for metals. We see we have arsenic, cadmium, and cobalt, which are more than the baseline. And then we have HCB and the PCB. I remember the first one, they also found, they also found HCB and PCB having some significant association to some extent. So that's confirming. Okay, but there are other Bayesian methods to handle similar problems. For example, multiple groups or regularization, right? Yes, there is hierarchical BKMR, which is been proposed, and it's been quite popular actually in this particular field, and takes into account different mixture components and account for correlation structure. All right, then what are the potential advantages of the limitation of using either methods? So let's do some simulations. So I did some simulation on the simulation correlation matrix. We have, in the simulation, we have 4 different groups, each group differing sizes. The first group has a size of 5, second group has 6, 7, the third group has 7 size, and then the fourth group has 8 different components. Now you see how I similar to this data is within these groups, the correlation is very high. And between the groups, there is correlation, but not that high. And the outcome is a linear combination. Okay, everything I'm doing is in a linear framework here. So the outcome is a linear combination of these groups with some predefined coefficients. Now, what are the coefficients? I took the coefficients in such a way. So these are the different exposures or different groups. We have 4 groups here. Some of them are, so the first 2 are very high, and last three or the last ones are like very small exposure, like very small values, so that we can actually see this pattern. So very high, small, small values, then very high, small values, very high, small values, just like that. And then we have negative, positive, negative, positive. So this is how I assumed our coefficients. What do you actually see here? On the left side, we have the results from the penalized BWQS that I am working on, and then the right side of the hierarchical BKMR. This is a heat map of almost like 500 simulations. So you see the first two groups, you remember they have very high values. So on the left side, we actually see like two very strong indicating lines, and the red ones are higher values, the yellows were the small values. But for the hierarchical BKMR, what is happening, it eventually chooses one chemical out of the two. Now that's what you see from this heat map here. It usually chooses one chemical within this two of them. Sometimes it does choose both of them, but mostly it chooses one of them. And then the rest is like pushed to zero here. And what is the result for that? The measuring performance in estimating the correct weights? Well, because it is not choosing both the chemicals, sensitivity, specificity, accuracy, it actually falls. You can see for hierarchical BKMR, it's not doing really great here. Penalized BWQS is doing to some extent pretty well, mostly because it is not choosing both the chemicals. And then the other part is we have also had the weights, like the estimates, the associations that we talked about, like this, basically this here, 0.6 or the small associations. What happens to that? So what I'm plotting is a coefficient for one quartile change. So the green one is the BWQS, and the left one is the hierarchical BKMR. And the red line that you see here, that's basically the true value. You'll see that the BWQS is obviously both of them are biased to some extent, but it's more precise and less biased than the estimates of hierarchical BKMR. And so the hierarchical BKMR has a tendency to go to near the zeros, but for example, for the penalized BWQS, it is still biased, but it's still near to the true value. But it might have some.
2 minutes left.
Thank you. It might have some public health implications. So it is very important to choose most appropriate statistical method so that we do not underestimate the true environmental risk. Because in this case, we might end up, if we end up choosing hierarchical BKMR, it might be we are underestimating the true environmental risk. So that is one of the limitations. But then, what are the major takeaways here? Our group BWQS is a useful approach which takes into account the overfitting and the group within group high correlations. Is basically an umbrella framework where you can have different type of LASSOs or different type of regularization based on your problem at hand. But group BWQS can be advantageous with respect to other available methods when there is only one, when there are more than one chemicals or major contributing chemicals or no major contributing exposure at all. But it might also be both hierarchical BKMR and the group BWQS may be performing really well when there is only one major contributing exposure. And the results are almost similar there and pretty much equivalent there. So everything that we are doing is in the linear framework, obviously, but if we do something in non-linear framework, we have to go to the hierarchical BKMR. So one of the things that the major takeaway that I want you to take from here is blind use of any exposure mixture method may lead to a very biased result. So we have to be very careful of choosing which method we are using. Future directions, since this is an umbrella framework and we can very easily incorporate the time varying data, and we can have the postnatal and the prenatal interpretable interaction terms. And this is my acknowledgement to my PI, Dania Valby and Elena. Thank you.
Many thanks, Vishal. This is also a very nice presentation and very nice approach. I don't see any question or comment on the chat for the moment, but maybe I can ask you how time consuming is these methods?
Sorry?
Do you need a lot of time to apply this method in your computer?
Not really.
Or do you need any other, no?
Not really, because everything that we are doing is through STAN, and so it takes almost similar to a little bit less than the hierarchical BKMR, similar time. So in time constant, we are almost that parallel.
Good. May I ask the same question as Léa before about dealing with categorical exposure? Do you can you include some?
You can deal with categorical exposures. It's basically eventually you're modeling a linear model, so you can handle categorical exposures.
Good. No question for Vishal from the audience? Not for the moment. If not, I think we can move to our next speakers, who is, and thank you, Vishal, for your presentation. So our next speaker is Anders Wilson from the Colorado State University, who will present something, a presentation about the Exposome-Health Association study using Bayesian 3 distributed lag mixture models. That seems very interesting. So, Anders, the floor is yours.
Thank you. Are you okay with this? Can you see the slides?
Yeah, perfect.
All right. So this is joint work with PhD student Dan Mork, who this is part of his thesis, and he's really done all the work on this. So basically, the idea here is we're really interested in estimating the association between repeated measures of exposure and an outcome. So our method is really made to look at these repeated measures as the key part here. We're going to use a BART style model, so a Bayesian additive regression tree style model that fits a really simple interpretable parametric model. And we're going to use the trees to add structure in the effects of the repeated measures over time. And it's also going to perform exposure selection of the main effects and interactions in our model. And so it's based on this paper here, which is up on arXiv, if you're interested in more of the technical details. So what is this method intended for? Well, its original intent was to think about sort of repeated measures of exposure, such as weekly exposures to multiple pollutants throughout pregnancy. And so this is from Dan's paper here, and you can see some results from it. But he estimated the association between birth weight per gestational age z-score and 5 exposures for air pollutants and temperature. And so these are sort of the typical distributed lag effects that I think a lot of people are used to seeing. But the idea here is for PM, you can see that there's a negative association between PM and birth weight during the middle part of pregnancy. Similarly, we get what's called a critical window for temperature in the later part of pregnancy. But it's not just an additive model. So key is that we get the full interaction surfaces between these. So we have these repeated measures here, and this is the estimated interaction between PM and temperature. And so you get things like, exposure to PM at week 20, well, there's an interaction between that exposure and temperature at week 20. But there are also these time delayed interactions as well. So he identified that there's an interaction between PM at week 20 and say temperature at week 30 as well. So you get this sort of priming idea you can play in, or time sensitive interactions. And we're doing this by fitting this sort of simple model here, simple but big, where we have M exposures, each measured at T time points. And here we get the linear effect of the main effect of every exposure at every time point, plus the pairwise interaction between every exposure and every other exposure at every single combination of time points. So we get a full interaction surface like this for every single exposure. And then we're parametrically adjusting for confounders on top of that. So you might look at this model and say, well, that's just a regression model, a GLM or a linear model. What does this have to do with trees? And so we're using trees to sort of construct this distributed lag effect over time. And so I won't go into the super technical details of this, but the general idea is we're fitting a bunch of binary trees that partition the time domain. So in that previous example, the time domain was 37 weeks of gestation. We might fit a tree that partitions it, like is shown in this picture, into 3 segments, about trimesters. And every single segment of time has a constant effect. So this is the effect during this first time segment. This is the effect during the second time segment, and the effect during the third time segment. And these trees are learned from the data, so we can get trees that divide it up into smaller time segments, or ones that don't divide it at all. And so if we don't divide it at all, we're essentially putting average exposure throughout pregnancy into the model. If we do something like this, we're basically putting trimester average exposures into the model, but it can also adapt to the data and do other partitions. And so we're using this sort of instead of splines in this model to construct this structure over time. But we're also using tree pairs. And so you can think about these 2 trees as being paired. This one divides one exposure into 3 segments, and this one divides another exposure into 4 time segments. And then we can interact those and get that interaction surface that is also parametrically small. We only have here, 9 different effects, right, for each of these interactions. We're just interacting cumulative exposure over each of these segments with each other. And so we're using the trees to split over time. Each time segment has this constant effect, and the interactions are just defined by interactions between these 2 time segments. The tree structures are learned from the data, as well as the exposures that these are applied to. So you could think about this being applied to PM, and this being applied to ozone, or this being applied to PM, this being applied to temperature. And so we can get different interactions and different main effects in that way. And then, like all BART models, we're going to use an additive ensemble of these. And that allows us to have nice, smooth distributed lag functions. It allows us to learn about different combinations of exposures and interaction terms that might be in the model, and what exposures might be in the model. And so clearly, this is designed for a situation where we have a lot of measures of exposure, like this weekly exposure throughout pregnancy. And so this is the intended use of it. We have a lot of time points, but maybe one or a handful of exposures. The question now is, we thought this was an interesting, what happens if we try to just 2 time points, but a whole lot of exposures? Will this approach still work, and how will it behave? And so we thought that was an interesting challenge here. So what's gonna happen when we apply this to only 2 time points? Well, the exposure can enter the model in 2 ways. So if we have exposure that's measured prenatally and postnatally at 2 time points, it can either enter the model as 2 separate predictors, one for each time point, or it can enter the model as a cumulative exposure or a single predictor that's the sum of those. So essentially, if a tree splits, we're going to have the model will enter 2 predictors, prenatal exposure and postnatal exposure. But if the tree doesn't split, we're going to just enter in cumulative exposure over both time points into the model as our single predictor. And so when we think about the exposome, this is a form of dimension reduction where we can reduce the dimension of our predictor space by collapsing over time. We're going to have all pairwise interactions into the model, and the pairwise interactions use the same measure of exposure. So if we use only the cumulative exposure for the main effect, we're also going to get the cumulative exposure used for the interaction effect. And so this too does a lot of dimension reduction here. The approach also selects exposures in and out of the model, so we can completely remove exposures from the model. And this is done sort of at the group level. So we're not selecting out a single time point, we're selecting out an entire exposure at all time points, or including exposure at all time points. The interactions, it's hierarchical selection for the interactions. So we only get an interaction in there if both main effects are included as well. And then finally, there's a small amount of shrinkage applied to the effects through the prior structure. So we get some shrinkage on top of this. Although selection is probably, and the collapsing over time is probably the stronger regulation approach we're using. So we tried this on the Exposome data. We used the BMI-Z outcome. We put in a handful of covariates, the cohort, gestational age at birth, maternal BMI, weight gain, a few others. We used 56 exposures measured at 2 time points. So our primary screening method was to find exposures that were measured at 2 time points, because this method is really designed for repeated measures. So we were looking for that. So when we do that, we end up with a possible 1,540 pairwise interactions. So that original linear model I showed becomes a big model. And if we think about all those main effects and interactions at 2 time points, that model would have about 6,000 parameters in it. So it's a pretty big predictor space we're using, even with this subset of 56 exposures. So what do we get out of this model in the end? Well, the first thing we get is we get estimates of variable selection. And here I've shown the posterior inclusion probability for each exposure. So you can see along here all the 56 exposures that we included. We do get an equivalent Bayes factor. So if you prefer sort of a more formal measure of this, you can use the Bayes factor. We don't get that for interactions. So I shied away from focusing on that here. And so there are a handful of these that jump out as being included with very high probability. And included means it's included in at least one tree pair in the model, right? So HCB, PCB 170, DDE, MO are included in almost every iteration of our model. So extremely high probability. And then several others that are included at least half the time. And I'll come back and look at the effects for these later.
2 minutes left.
On top of that, we also get posterior inclusion probabilities for the interactions, right? And so we had 1,500 of these. And so as would be expected, there are a whole bunch that are near zero. We're selecting out the vast majority of these with very high probability. But we do get this tail up here where we get some that are included with fairly high probability. And so zooming in on that, you can see here they're the same ones because we have this hierarchical variable selection. We can't have an interaction effect that has a higher inclusion probability than the main effect. But we do get a few interactions, particularly around those first few exposures, HCB, DDE, that are included with high probability as well. And so when we interpret these, it's not a specific time point, it's whether this exposure is included at all. And so it could be included and collapse down to a single measure of cumulative exposure, or it can be included as multiple measures of exposure, and one time point might be important. As you'll see coming up here, there's also not a one-to-one relationship between being included in the model with high probability and having a significant effect using traditional significance standards. So being included tells us this variable is important, but that doesn't mean we can estimate the effect well. So here are the effects estimates of the main effects, right? And so as I was alluding to there, most of them are null. We didn't find much that were significant in terms of at least significant in terms of the 0.95 credible interval not containing zero. We did find this negative association between DDE in the postnatal period and BMI. We found pretty large estimates here, but with high variance for HCB and MO as well as others like population that were included a lot of times in the model, but seemingly have near null effects overall. We can also look at the interactions here. And so when you read these, we're looking at the interactions between all 4 pairs of times. And so if we look down here at the one that obviously jumps out on our screen, we have, this is the interaction effect between prenatal exposures. This is between prenatal exposure and postnatal exposure and vice versa, MO being on this axis and HCB being on here. And then between the postnatal exposures. So we do find this interaction between prenatal MO and postnatal HCB here, which is significant, although in positive. And that might play into the fact that we had those very large effect estimates, including large negative ones. So it might be countering out that large effect estimate sum. But we also get some interactions that are included a lot, but seem to have very little to no effect. So the dot estimates 0.95 significance based on the credible interval. So nothing else is found significant by that measure. And these ones particularly are extremely flat as well. So thinking about this method, it's certainly most useful when exposures are observed with many repeated measures of time. So that's what it's designed for. This is a little bit out of its wheelhouse here, doing 2 time points, but it did seem to work, and it to some extent here. It allows for quadratic main effects in all pairwise interactions. And so I think something I didn't mention was, right, you can have an interaction between a pollutant and itself, right? So we can interact HCB with itself, and then we're getting both an interaction between HCB prenatal and postnatal, but we're also getting those quadratic main effects. The interactions can be those time-sensitive or time-lagged interactions. So if we're looking at exposures throughout the life course at 2 or more time points, I think that's a really important thing to consider, the possibility of priming or 2-hit hypothesis. It works with P bigger than N. So in this case, right, we didn't have more exposures than the sample size, but certainly when we count up our parameters in the model, it was significantly larger than the sample size. In terms of limitations, there are no higher order interactions. So you only get the pairwise interactions. And we don't get the highly complex exposure response functions, right? We're limited to a quadratic main effects and pairwise interactions. So we're really fitting a polynomial model. It's computationally efficient. Dan's coded this up really nice in RCPP. We fit it with an administrative cohort of 300,000 individuals. We've tested it out to about 60 exposures, each observed at 37 time points. So it scales both in terms of time point, well, all 3 in terms of time points, number of exposures, and sample size there. And so you fit these models on the order of minutes to maybe an hour to fit these models. So it's pretty efficient. And then it's really easy to interpret, right? It's just a polynomial. So we can interpret these parameters really well. I think most people who work in this field have had at least one course that teaches us how to think about those. And that does it. So it's based on this paper here. You can find out more or implement it with Dan's GitHub package here. Some contact information. And thank you.
Thank you very much, Ander, for this presentation. It's great to see that there are some methods that can handle both repeated exposure and interaction. Unfortunately, we are running a bit out of time, so I will move now to the next speaker, and we will keep the question for you for the general discussion. So I'm pleased to introduce Chris Gennings from the Icahn School of Medicine at Mount Sinai, who will talk about evaluating a mixture effect of perinatal environmental exposure on childhood BMI using weighted quantile sum regression. So Chris, the floor is yours.
Good morning or good afternoon, whatever time zone you're in. I'm happy to be here today. Thank you for the invitation. And I think this is a fabulous opportunity to compare a lot of different methods. So there are a lot of different research questions that can be addressed with environmental mixtures. And the one that we're focusing on in this session is the idea of an overall effect. I'm going to frame that in the sense of, is there a mixture effect? And that's a pretty specific question. The concept of a mixture effect came from the toxicology literature with this phenomenon of something from nothing. So when the components are at very low concentrations, which might be relevant to environmental exposures, there may not be a significant association or measurable outcome, but it's just the fact that there's so many chemicals that are insulting us every single day that might provide this idea of a joint action where the components are sort of singing on in the same direction and showing the effect. So if we ignore the fact that there could be a joint effect, then we could underestimate risk. So the concept of a mixture effect is important for risk assessment. So several people have already talked about weighted indices, so maybe some of this is a bit redundant, but this is weighted quantile sum regression. We're empirically weighted indices. We generally split the data into a training set and a holdout validation set. Usually we put more in the holdout set for a little bit more power there. But the idea is to use a nonlinear, generalized nonlinear model to estimate the weights and the beta coefficients. The covariates are here, but where we've quantiled the exposures. And then we do this ensemble step where we can take bootstrap samples of the individual subjects, randomly selected with replacement, or we could take random subsets of the components. But either way we do that, at the end we average across the in this ensemble step to get the weights that we use to construct the index, and then apply that back to the generalized linear model to test for the significance with the beta 1 coefficient. And we can do that in a positive and negative direction by constraining the beta 1 in the nonlinear step. So this is a team of people that have contributed to this, but just a little bit of motivation about these different pieces or characterizations, I guess, of WQS regression. The reason we do the quantile scores is really to reduce the impact of outliers. Generally we see extreme values in exposure data, and so it bends those into having this reducing the impact. The ensemble step has been shown to improve sensitivity by breaking up correlation patterns and getting signals from different components within correlation patterns that might have the association. And we've done these simulations with environmentally relevant correlation patterns, and I think that's important for simulation work. So we had the bootstrap sample Caroline Carrico worked on, the random subset component Galabello and Paul Curtin have worked on. The directionality constraints are really to improve. It's one more constraint that can improve the ill conditioning because of the correlation pattern. So we look in a positive direction, and then we do another analysis looking in the negative direction. We don't have to worry about reversal paradox by doing that. And at the end of the day, we can put them together in a response surface. Additional extensions have been this repeated holdout idea that Eva Tanner has worked on that addresses generalizability of the results by splitting the data different ways for the training and validation. We can also check the assumption of linearity by doing a low S plot, which I'll show, of the covariate adjusted outcome with the estimated index, looking for curvilinearity. And because now we can estimate the weights with say a quadratic term of the WQS in a model or polynomial term, then we can actually think of that as a goodness of fit for the assumption of linearity. We've recently also included stratified interaction component of WQS, where we allow different strata to have different weights and different beta coefficients. And so I'll demonstrate that a bit as well. All this is implemented in the GWQSR package, which Stefano Renzetti has been primarily working on. Okay, so we're going to demonstrate this various pieces with the HELIX challenge data, as has already been done today so far. We're looking at the ZBMI across the 6 cohorts. We've got similar covariates, I think, to what other people have used. Here I'm combining the prenatal and the postnatal data together in the 7 different classes of chemicals. I have summed the DEH metabolites and summed the PCBs instead of representing them together. Now in hindsight, I wish I kept the PCBs separate, but that's the way it is. Okay, for analysis strategy, we always start with single chemical analyses just to kind of get a sense of what's going on. Here we had more generally negative estimates than positive ones. We also considered the idea of these 6 different cohorts. And so we started also with the WQS analysis in each cohort separately. We did find a significant negative association in each of the 6 cohorts, but there was no significant positive direction WQS index in any of the cohorts. So then we combine the data with adjusting for the covariates in both a negative and positive direction. We considered a repeated holdout, which I'll show you, and then we did a stratified interaction model with the in the cohorts, which is kind of interesting but complicated to interpret. So the positively and negatively constrained WQS. So we did this again in separate analyses, but in one case we constrained the beta 1 to be positive in the nonlinear step, and in the second case we allowed it to be negative. And again, the index itself was not significant in the positive direction, but it was highly significant in the negative direction. And here we did that test of linearity by doing a goodness of fit test, meaning that we allowed for a quadratic term in the WQS and it was not significant. So we're say that there's no real evidence of nonlinearity there. The interesting thing about doing this though is we can now look at putting these 2 indices in the same model. Here the covariates of all the continuous covariates are centered, and if we interpret this at the reference level of the categorical variables, then what we see here is an approximate response surface where you see there is a strong negative association and not much of a positive one in terms of the mean BMI. So, okay, what are the components then that are associated with these 2 different weights? So what you see here is across the top row is a common analysis in the positive direction. Across the bottom row, there's a common analysis in the negative direction. I've separated these just for sort of interpretation between the prenatal and the postnatal. In the top row here, it's not a significant relationship, but the primary weights went to the postnatal exposure. So these aren't significant, the weights aren't significant, so we don't want to overinterpret that. In the bottom row, though, this is a significant relationship in the negative direction. Most of the weight went towards the postnatal period. And then what I've done here is just I've created what I call here relative weight. So I've divided each of the estimated weights by the proportion of the weight of the total to get the relative weight just for a comparison. And I think we're getting similar results to some of the to what others have shown with the HCB. There's the PBDE back here, and then some of the metals as well. But that analysis is just we do the ensemble step, but it's only one split, a 40-60 split with 40% in the training. Using Eva's method with the repeated holdouts here, I've done 30 different repeated holdouts. And what you look at on the left side, this is only in the negative direction, but if you look in the left side, these are, you see the histograms, the little bar charts there have to do with how many of the 30 repeated holdouts had a indication of an association by where the weight was estimated above the cutoff of equi-weights. And so you can see there's some color there across the different, you can see this metals, the different categories down here. And then we have a box plot embedded there, and that's the distribution of the estimates across the 30 holdouts. And then the diamonds are the mean weight overall. So what you see is these are not relative weights, these are just weights themselves. But what you see is that really the more larger weights are in the postnatal period, which is what we saw before. But interesting here, and I think some of the previous speakers have seen this as well, we do have associations like this is interesting, the PVD 153, it was always detected at to be above the equi-weight level, but the estimates itself are very low relative to something like HCB and the sum of the PCBs there, and this is the DDE, actually have a wider variability, but weights that get to be kind of dominant. And then out of the 30 repeated holdouts, we get beta estimates, and here's a box plot of the distributions there. You can see they're all away from 0 in a negative direction.
2 minutes left.
Thank you. So now here's, just when she says this, now we got 2 minutes. the stratified interaction. So we get here, I'm allowing for different weights per strata for these 76 different components in the prenatal and postnatal. And what we see is something kind of interesting. It looks like that the first cohort is sort of dominating things. The other 5 cohorts are sort of have a similar association. Now the range of the WQS here is limited because nobody can, you're limited, they all sum to 1, but nobody can be, but their portion of the cohort of the total strata. So seems to be a distinction between the first cohort and the others. This could be due to different, this is average concentrations across the different cohorts. And you can see, sometimes it's orders of magnitude in terms of average values. So that can also play a part in terms of what the slope might look like. These little spaghetti plots are complicated to look at, but largely we're seeing in the pregnancy exposure, there's not a lot that kind of get above that guideline value, where we see more here, but largely it's the first cohort, but we do see some others that are peaking above that. Again, this is just a guideline. It's not meant to be yes or no about what's important, but I think it's going to be hard to interpret this, the interpretation, to really dive into that to figure out, or is it really the exposure pattern that's changing these slopes, or is it the something about the concentrations there themselves. So that's complicated to interpret, but these are highly significant changes of slope between the among the 6 cohorts. So what we've done then is focus the WQS regression, where we're trying to estimate a mixture effect to detect and characterize that mixture effect. With the repeated or the random subset, we can consider the case where P is much bigger than N for like metabolomics and microbiome data, which is what we're doing lately. We can do the stratified interaction, which has been very helpful with sex stratified things. And then the repeated holdout, I think, is important for generalizability of results, but it takes much longer to run than the other analyses. As has been already stated, of course, WQS is not focused on looking at interactions because it can't do it. The curvilinearity, we're limited to low degree polynomials. We can't get something that looks, more sigmoid shape or whatever from that. We do split the data. I think that there's an advantage to splitting when we have significance after splitting. I think that's a really strong result because you've got that holdout set that you're testing the significance in, but we do have a reduced power by doing that split. Future directions, we have recently published the lag WQS version, and then Paul Curtin has been working on the LWQS-R package, which has recently been published. So as I say, it takes a team, and I really appreciate all my colleagues here. The only person I haven't mentioned is Elena Colacino, who's been working on that Bayesian WQS version. So thank you very much.
Thank you, Chris. And I have to say that it's impressive to see how fast the extension of the WQS are coming. And I don't see any specific question for you on the chat, but I have one. From the beginning of the session, we did not discuss about missing data. And I was wondering if you are planning to do an extension of the WQS that may handle missing data, or if you can recommend to use repeated outputs, using multiple imputed data set or
yeah.
Similar.
We haven't published anything with a multiple imputation, but we have done that. Eva did that particularly with some COVID related data. I think there are people, I think David Wheeler's group at Virginia Commonwealth University has done something with multiple imputation, but it is possible to do that and then do the WQS, in each of the multiple imputed data sets and then look at the variability across those. So yeah, I think that's an interesting extension.
Thank you. And Chavi Basagania, also a question, and is wondering if, another question. Is the sample size enough to do the partition of the data, or we will really need larger data set to detect some association?
I don't think there was any problem with this challenge data set. I mean, we have been doing analyses of, 100 kids or something in an analysis, and that's just not generally going to be enough. You end up having more parameters than children. It is, again, I think there's a value to it when you can find significance, but you do lose power by doing that. We always look without the split if the sample size is small, just to see if there's any indication of something going on, but we prefer the split.
Okay, thank you, Chris. So let's move to the next speaker, Shunak Chattopadhyay. Sorry if I mispronounce your name. From the Duke University in the US, who will talk about synergistic interaction detections. So Shunak, the floor is yours.
Yes, so I'll get started. If you can see the screen.
Yeah, perfect.
Okay, sounds good. So I'll be talking about this synergistic interaction detection, which is a joint ongoing work with my advisor, Professor Johnson. So the background would be, we're focused on modeling dose response surfaces in the presence of interaction. Most of these joint modeling approaches, they can't really incorporate prior information about interactions. And so we would like to have a flexible model where we can have some sort of prior information about these interactions. And in our specific setting, they're present as either the possibility of a synergistic or an antagonistic interaction between exposures. That's what our prior knowledge is present as. So let's dive into the formulation. Suppose we have a continuous response Y, and we have exposures X1 to XP, and we have a set of covariates Z. And so we're going to, have each of these terms. We're going to have a covariate effect as a linear term, and then we're going to have a sum of main effects for each exposure. And for the interactions, we're only going to consider two-way interactions, so only bivariate functions with these HUVs are the interaction for the Uth and Vth exposures. And so all these HUVs are assumed to be non-negative, and they're multiplied by a sign beforehand. So each interaction between any two pair of variables is either non-positive or non-negative. We're going to call the non-negative interactions as the synergistic ones and the non-positive ones as the antagonistic ones. And so obviously a main modeling assumption here is to assume that the errors are Gaussian with mean 0 and variance sigma squared. So we can also estimate these coefficients, gamma UVs, but they're in general time consuming because you have p choose too many interactions, and it's the usual problem with variable selection, which it tends to grow. P choose 2 grows pretty fast with increasing P, so it's time consuming. So about the model specification, this is mostly about just making the previous model that I described workable in a setting. And so we have to, in general, in these models, identifiability is an issue. And so in general, people assume stuff the integral of the main effects is 0 for each of the main effects. And they also assume that, any sort of pairwise integral of the interaction is 0, which we couldn't do here because the interactions are either non-negative or non-positive. And so imposing such a constraint would impose the interaction to become 0 overall. So we kind of merged two identifiability conditions. We impose that the interaction between variables XU and XV start from 0 on either axis. That's what our imposition will be on the interactions. And so once we have these identifiability conditions, you can, for each of the FJs and the HUVs, we're going to assume a B-spline expansion. So for the FJs, we have this B-spline expansion where the coefficients have this Gaussian prior, where lambda j's are local coefficients. And for the interactions, we model each of the interaction, the value of the interaction as a squared function of some underlying flexible function, capital H UV, which again is expanded as a tensor product B-spline representation, where the coefficient vector is again given like a prior that has both a local component, like through the delta UVs, and a global component. So these matrices sigma and S used in the main effects and the interaction effects respectively, they're suggested in Lang and Bresler's paper about Bayesian P-splines. They work pretty well in most simulation and the application result. And so like the tau square parameter signifies shared information between the interaction, while the delta UVs are like regard the local information about interactions. And so we're going to sample from the posterior using a metropolis adjusted Langevin algorithm within Gibbs approach. So for like the mala is required to sample from the posterior of these interactions, which are definitely not like conditionally conjugate. And so like key goals, our model is flexible enough to incorporate prior information in the form of synergy or like its opposite. So what we would really like to know is that whether there is at all a synergistic or antagonistic reaction. And so we would like to have a flexible prior on the class of interactions. And this is precisely what the delta UVs allow us to do, because we're putting a heavy-tailed half-Cauchy prior, as is done in like horseshoe methods and stuff, to shrink them to 0 if there is no interaction. So that's goal 1, and goal 2 would be to provide a point estimate of the interaction surface along with accurate uncertainty quantification. Obviously, we can model more complicated and nonlinear bivariate interactions because we're using splines. So if we look at the exposome data set, we consider the birth weight as our response, Y. And obviously, like a limitation of our method is that we can't really consider categorical exposures. So we are only going to have to restrict ourselves to a few continuous exposures here. And so the birth weight appears reasonably Gaussian. So that validates our model assumption kind of. Also, to get rid of extraneous variance, we only consider the subjects with gestational period greater than equal to 37 weeks, which is the usual cutoff. And so our sample size is then going to be 1,234. So the covariates are more or less the usual that people have assumed, I guess, some of them at least. So we have like a linear covariate effect, as we saw. And the exposures, we're going to take 3 exposures. We're going to work on, we're still working on extending this to a greater number of exposures with faster computational speed. So we consider the sum of PCVs, DD exposure, and P4 exposure. And we will try to see if there's any negative interaction between these exposures, because lesser birth weight in general is harmful. And so we standardize the data prior to fitting the model. And also all of these, the whole model requires the exposures to be in the range 0 to 1. So that normalization also had to be done. And all the interactions were fitted with a -1 sign. So let's look at a summary of results before we look at some plots regarding the main effects and the interactions. So the covariates pre-pregnancy BMI, maternal weight gain, and gestational age at birth, they all had positive effects on birth weight, as you would expect, while smoking had a negative effect. But in the data set, it's not super clear whether it's the mother who smoked or the father who smoked. It's just given as either one parent smoking or both the parents smoking. So anyways, we converted that into a binary of either no smokers or at least one smoker in the family. And that had a negative effect on birth weight. For the main effects, the sum of PCVs seem to have a slight positive effect, or for very high PCV range. So it's all in the log 2 scale. So for in the range around 8 to 9, which is pretty big PCV exposure, it seemed to have a slight positive effect on birth weight. Exposure to PFOS in the range 0 to 2 in the log 2 scale have a negative effect on birth weight, while like for the DDs, we didn't really find there's to be like a significant effect on the birth weight. And for the interactions, it seems only the sum of PCBs and P4 have some like noticeable interaction for large values of the sum of PCBs, and more or less like moderate to large values of P4. And so also like the sum of PCBs and DD exposures, they had this slight estimated interaction. Again, negative for, like both large values of the sum of PCBs and the exposure to DD. And so let's look at the main effects. So if you can see the main effects, it's kind of like for the PCBs, for the P4s, there seems to be this this negative area where P4 is like having a negative effect, and for the PCBs, it seemed to have a slight positive effect around here. But for the DDs, it's more or less doesn't seem to directly affect birth weight. And finally, if you look at these interactions between PCBs and P4s, the other two interactions were mostly zero, as I mentioned, but PCB and P4 seem to have an interaction. So it's important to keep in mind that there's a negative interaction. So I've just plotted the negative of it to show it in a like a convenient axis. So the maximum estimated interaction here is around 0.38, and that had a 95% credible interval of 0.23, which is the 2.5% surface that's plotted here, and the 97.5% quantile of this interaction surface, which is 0.73. So there seems to be some presence of negative interaction between the sum of PCBs and P4 exposure, which could be analyzed even further. So that's all I have for now, and thank you. So if you have any questions, do feel free to ask.
Many thanks, Shanak. I don't see any question on the chat. Maybe I have two. I can ask you maybe one. Can this method be extended to more than 3 exposure? On how many exposure can you look at?
Yeah, so we're in the progress of having like an efficient RCPP implementation of the whole thing. Yeah, it can be in principle be extended to any number of exposures, but we were just trying with these 3 because these 3 had some promise. In simulations, we've tried around 10, 15 of them, but it's still an ongoing work. So I'm still trying to make things more computationally efficient. Yes.
Okay, thank you. I don't see a question on the chat. I think we will move to our last speaker, and I will keep my question for you for the general discussion. So our last speaker is Matthew Corley from the Virginia Commonwealth University. We're going to talk about exposome analysis with Bayesian group index regression. So Matthew, the floor is yours.
All right, and can everyone see my slides?
Yeah.
Excellent. So good morning or afternoon, as the case may be. Today I'm going to be talking about exposome analysis with Bayesian group index regression. This work is done in collaboration with Dr. David T. Wheeler at the Virginia Commonwealth University. So the Bayesian group index regression model, similar to some of the other index regression models we've seen today, was developed to handle highly correlated data. We have here the generalized expression for the model with a binary health outcome. On the left-hand side of the equation is the logit of disease probability, PI. We then have beta naught or intercept, and the first summation on the top, capital K, is the number of indices we're including in our model. Betas 1 through K are the effect parameters for each index, indicating the cumulative association of that index's predictors with the outcome. Multiple indices allow for differing magnitude and direction of association with the outcome. Within each index, in the parentheses, we have capital C underscore K. That's the number of predictors in the kth index. WKJ is the weight parameter for the JAFE predictor in the Kth index, representing the relative importance of that predictor in the index. In our model, the index's weights are constrained to be between 0 and 1, and all weights in an index must sum to 1. The QKIJ is the quantile score for the 8th subject within that predictor and index. The raw score, the raw data is transformed into quantiles. This is to reduce the effect of outliers and account for varying concentration scaling in different predictors. Any quantile specification can be suitable. In our analysis, we're going to use quartiles. And in the last term, we have ZI transpose, which is a vector of covariates with their effects phi. The priors on our model are we use very vague normal priors with a variance termed precision drawn from the uniform 0-100. And the index weights are given a Dirichlet prior, which is convenient in that it assures that our constraint on the weights I previously mentioned hold. Monte-Che and Monte Carlo is used to estimate the model parameters. So for our analysis of the data, we modeled child asthma risk with predictors from the air pollution, indoor air, metal, organochlorine, pesticide, PBDE, PFAS, phenol, phthalate, traffic, natural space, meteorological lifestyle, and built environment families. So I'll note that we used the longest time variables for the air pollution and meteorological indices. And we restricted our analysis to childhood measurement variables. We excluded maternal predictors. So in the table below, you can see we have betas 1 through 19. These are all the indexes. And we got to 19 indices by taking each family group and then splitting them based on their direction of correlation with the outcome. So we calculated all of the univariate correlations between all the predictors and asthma. And if you look at, for instance, beta 2 and 3, we took the indoor air family and split those into negative and positively correlated, where absorbance and NO2 went into beta 2, and PM and benzene went into the beta 3 index. Doing this left us with some singleton predictors. So that would be a predictor that had an index that had all positive correlations, but one negative standout, and we would drop that. In our main model, we dropped PCB 118 from the organochlorines, DMTP from the pesticides, PFNA from the PFAs, TRCS from the phenols, and temperature from the meteorological family. And our controlling covariates were cohort, child sex, and maternal age. So this is the odds ratio estimates for our main model. We had significantly negative associations with asthma for the pesticides, PBDE, and lifestyle minus indices. And within the lifestyle minus index, we have our weight plot, which shows the KidMed and sleep time predictors. The weights for these were 0.57 and 0.43 respectively. That indicates that KidMed is responsible for a slightly greater proportion of the protective effect of that index. And of the covariate effects, cohorts 1 and 2 were significant and positively associated with asthma, as was child sex, with boys being 1.63 times as likely as girls to have asthma. So the significant cohort covariates indicated effect modification. So we then ran further analyses stratifying by cohort. Cohorts 3 and 6, however, had very few asthma cases, and that resulted in highly variable parameter estimates. So therefore, we're going to focus on the results for the other cohorts. These cohort models were developed in the same way as the main model, taking family groups as an index, but then splitting them if there were mixtures of positive and negative correlations. This led to some slight differences between model specifications. As an example here, between the main model and cohort 1 model, the main model is quite much larger, has 19 indices, and the air pollution predictors were all together in one index. The cohort 1 model had 202 subjects, 20 indices, and we split that air pollution index into a positive and negative index. Child sex and maternal age covariates were included in each cohort model. So in the interest of time, I'm not going to present the full results for each model. This table summarizes all the significant findings from cohort models 1, 2, 4, and 5. Some of the findings here, we're presenting the odds ratio, the 95% credible interval, and the most highly weighted 1 or 2 chemicals in that index along with their weights. Some of the findings we have are supported by previous publications. For instance, cohort 1, the phthalates plus index, was estimated to have an odds ratio of 2.99, and its most highest weighted predictor, MEP, has been previously associated with asthma in a 2019 study. In cohort 4, natural spaces had a protective effect with an odds ratio of 0.21. The relationship between green spaces and asthma has been debated in the literature, but there are similar findings that have been published. The green and red highlighted findings are indices that have a particularly heavily weighted predictor, and I'll go into more detail with those weight plots in the next few slides. So in cohort 1, we had a significant finding for the metals plus index with an odds ratio of 2.39. And the highest weight and the dominant predictor in that index was manganese with a weight of 0.55. This finding is backed up by literature, as manganese belongs to a group of agents called transitional metals that are known to induce what's called occupational asthma. So that would be a finding of interest, worth more investigation. Also in cohort 1, we had the phenols plus index, which had an odds ratio of 2.23. OXBE is the most important predictor in this index with a weight of 0.75. I couldn't find any literature talking about OXBE and asthma, but BPA is previously been found to be associated with asthma and is in the same chemical class. So again, probably something that further analyses would be interested in. In cohort 5, the traffic index had an odds ratio of 2.03, and the highest weighted predictor was traffic density with a weight of 0.79. Automobile exhaust and traffic density have previously been linked to childhood asthma. And a related finding in cohort 5 was the built environment negative index, which had a protective effect of 0.17, with home access points being the dominant predictor with a weight of 0.67. Home access points is the number of bus stops within a 300-meter radius of the child's home. And this aligns with the traffic density finding, as an increased use in public transport and therefore less private automobile exhaust has been found as well to be negatively associated. Finally, as an extension to this analysis of the Exposome data, we tried to incorporate some omics data. So we took the main model that I described previously, and we incorporated the serum metabolomics data. So in addition to the 19 family indices, this model includes biogenesamines, amino acids, isocarnitines, glycerophospholipids, and sphingolipids. And each of those were split into a minus and a plus index. The largest of these indexes had 25 predictors. And of them, the only one that was significant was isocarnitines minus, which actually had a positive association with asthma. The top two metabolites, 40 and 8, had weights of 0.132 and 0.192 respectively. This has some support. This finding has some support in the literature. Isocarnitines are generally associated with inflammation. More specifically, they have been associated with non-steroidal anti-inflammatory drug exacerbated respiratory disease, aka NERD, and it's a chronic inflammatory condition. Some general strengths and limitations of our model. Strengths are that by using the Bayesian framework, there's no need to split the data, which helps use all your sample size to power your study. It's also quite flexible. We're able to incorporate imputation of missing data. That's one thing I looked into but haven't presented here in the interest of time. You can incorporate spatial random effects and time to event data as well. And some limitations in our model, we can't look into interaction effects, and that was, I think you could see in the stratified analyses, something we had to have a recourse to in lieu of that. And So that is my presentation, some references, and I'd be happy to take any questions.
I thank Matthew. It was a very nice presentation. You have one question from Nikos Stratakis, who is asking, could these indices be used for further validation in another data set or in another cohort?
Yeah, you could use the same indices. The choice of index, the number of indices and their membership is an open question. In my analysis, I was relying on the family specifications and then those univariate correlations to decide on splitting the indexes. But having a more sophisticated empirical measure of how you want to group things is something we're interested in looking into.
Thank you. So now I will invite all the speakers from this session to turn on the camera if they agree. And we will have 10 minutes left to discuss about this session. And maybe I would like to highlight one comment made by two different persons from the audience who were suggesting that who realized that from the different presentation from today, most of the association with chemicals were observed with persistent chemicals, and they were wondering if error measurement of the exposure may affect the selection of the most persistent chemicals. So I don't know if one of you want to comment on that, or
I don't know so much about for this data set, but we have seen some interesting results with thyroid analyses with persistent and non-persistent, where they actually went in opposite directions. So I don't think the methods are limited to just highlight the persistent ones. And also, I think the experience with the non-persistent is that it's sort of behavior patterns make them almost persistent. They may not stay in your body long, but you're certainly exposed to them on a regular basis based on building things or behavior of what's, how you live your life. So.
Yeah, thank you, Chris. I think another comment that we did not answer previously was about the fact that some people only focus on chemicals in their analysis, even if some other also include external, what we call external exposome. And so the audience was wondering if there is some difficulty to merge this different kind of exposure from chemicals to external exposome or not. I think Vishal made some comment on this in the chat.
Yeah, one of the perspective, we started the analysis with multiple different other groups or indices, for example, built environment and or air pollution measures. But there was always an issue of over-adjustment bias. So that is something that should be taken into account while interpreting the data. We can obviously model them, but the results that we are obtaining, does it make much of a sense or not? So we can add a lot of things. So yeah, that's my comment.
I agree. The interpretation is what's important at the end. Does it make sense to have these things together in an index? So if you're looking at environmental exposures, that's, you're thinking about a mixture effect, which is a biological thing. If you're adding external things to that, you could think of it more as a exposome-wide sort of index, which is a little different than just the biomonitoring. But I agree with Vishal. I think it can have some issues as well.
And maybe something I also want to discuss with you was about the interaction, because usually we don't find complex interaction in our analysis, but do they really exist, or do we need larger data sets to detect them? What is your opinion on that? this is not an easy question. And I think no one's have the answer yet.
So my sense of that is there were many years in my life when I focused mainly on looking for synergy and looking for things like that in toxicology data and that. But I moved away from that when I started thinking about environmental exposures being to thousands of chemicals. And so I got to the place where I was more concerned about the denominator, how many chemicals that we're exposed to. There's always the possibility of an interaction, but I think I'm more concerned about the number of exposures and methods that can accommodate that than I am the potential for an interaction. It could become worse with an interaction, absolutely. But when you think about all the endocrine disrupting chemicals we're exposed to, that's my focus is how do we get, how do we do stuff to get rid of some of those toxins?
Yeah, I agree with you. Anyone else want to comment on that?
Sure. I think one of the difficult things about interactions is just the power it requires to estimate them. As much data as it takes to estimate a main effect, it takes a lot more to characterize an interaction. So even if there are really important ones, it's just, you require a lot more data to characterize those really well. And so I think that's just a limitation of looking into interactions.
Yeah, totally agree. We need more money to include more individuals and to measure a lot of chemicals or other exposure in a very big population.
Can I just add though, in terms of interactions, in terms of risk assessment methods, if you're underestimating risk because you're assuming that things are not interacting, so you're assuming additivity, but in fact there are some important synergies that you're not accommodating, then you're really underestimating risk, and that's a problem. So I think there is a place maybe in the toxicology literature as well to look for interactions. But in epidemiology data, I think it, like Glen says, it's really hard to get the power for that, I think.
Yeah, it's true that using the toxicology data that may find some interaction and then using epidemiological data to confirm this finding from toxicology could be the good approach. Maybe another thing that I would like to highlight is that some of you choose to study BMI as an outcome, and one good thing is that almost all of you find quite the same exposure that were associated with BMI, like the PCB and the HCB, it's hexachlorobenzene, and the metals, and maybe this is a good point for us. And what is your opinion? Do you think that in our future papers, we need to provide results from different methods and to combine the result, or at the end, we just select a priori which method fit the best with our research question and just look at one single method without putting a lot of result in the same paper? The recommendation?
Yeah, I think replication with different methods is extremely important, as well as replication on different data sets. I think both provide increased level of evidence that's really important.
I'll add something here. I mean, every method has their own assumptions, and so I guess statistical triangulation is probably the best way to go, because in some of the methods we have some underlying interpretation issues also. So maybe if we can get one strong signal coming from all these 3 different or 4 different methods, that's helpful all the time.
Yeah, replication is the key. Glen, do you want to? Oh, yeah.
I guess it's also important, like given certain standard methods, like say BKMR, it's also important to measure yourself against that standard method. Like you would know you're going in the right direction. Like otherwise you would be picking up signals where there aren't any due to like issues with your method, right? Like that's what I wanted to say. Yeah.
Yeah. Any other question or comment that you want to say from the audience or from the panel? Any important message that you want to say or? No?
I like the fact that there's so much energy now with the exposome and higher dimensional things. I think there's some really smart people that presented this today that I'm really impressed with what they've done. And yeah, and like Vishal was saying, did you say method triangulation? Is that what?
Yeah.
So yeah, I mean, I think that's an important, is that a new phrase? I don't know. But I think that, when you see results that can be confirmed in other methods, it makes you feel good that, yeah, okay, we really are finding something. This isn't just method dependent. So yeah.
Okay, so I would like to thank you all again for your presentation. It was very great session with impressive work and amazing presentation. So yeah, don't forget to vote for our best presentation. And now, if you want, you can move to the special chat to continue the discussion and to meet other people and discuss on this topic. So thank you very much, and see you on the chat and on the next session.
Thank you.
Juan, I think you can start.
Okay, so that's fine. So welcome back to the next section, which is about multi-omics data integration. I'm really happy to see that the 4 selected sessions are covering 4 different aspects of multi-omic data integration. There are some supervised and non-supervised methodologies. And of course, there are also some talks linking to omic datasets, but also more importantly, there are other talks that are covering the integration of more than 2 tables. So this is very important, since we are generating different omic data in the HELIX project. So let's start by introducing the first speaker, which is Kyung Hu from the University of Maryland. He's going to present a new statistical graph model to systematically study association between multivariate exposome data and multivariate metabolomic data. So you can start whenever you want.
Hi, thank you for introduction. I'm sharing my screen now. Can you see my slide?
Yes, we can.
Great.
Perfect.
For this data event, we are proposing to use a new statistical graph model to systematically study associations between multivariate exposome data and multivariate metabolomics data. It's jointly worked with Dr. Shou Chen, Dr. Charles Marr, and Dr. Donald Milden from University of Maryland. For this project, we are focusing on the association studies in multi-omics data, which means we will discover the systematic association patterns between sets of multivariant correlated exposures and sets of multivariant metabolites or some other gene or protein expression data. And through these association studies, we can understand the human responses to a mixture of environmental exposures. Actually, we are dealing with a problem with multivariant predictors and multivariant outcomes. For this project, our goal is to detect the parsimonious multi-to-multi association pattern. In other words, we will identify or select sets of exposures and sets of accordingly affected outcomes, for example, the metabolites. And there are several ways to deal with this association analysis. For example, we can use univariate methods like multiple testing corrections, but these methods are based on a universal threshold. So the results may not reveal the underlying systematic association patterns due to noise or false positive and false negative findings. Another group of methods like dimension reduction methods, including principal component analysis, PCA, these methods are projecting the predictors into a new space and using the predictors in the new space to predict the outcomes. So these methods are limited to give the explanation of the effect of each exposure on each metabolite. And there are also some bi-cluster algorithms. These methods tend to assign variables into equally sized clusters, and in practice, they may miss the association patterns. So to address these challenges, we propose to use this bipartite graph model. So we are characterizing the relationship between exposures and the metabolites using a bipartite graph. We have a node set U for all exposures and a node set V for all metabolites. And we use this weight matrix W for the marginal association measures between exposures and metabolites. Then based on this bipartite graph, we tend to extract a subgraph of concentrated significant association pairs. For this plot, the left plot is a set of exposures in set U that have pairwise associations with a set of metabolites in this set V. And based on these pairwise associations, we want to detect a subset of exposures in U0 and a subset of metabolites in V0. If we consider these red lines as significant association pairs, then we want to detect such a subgraph or this subset U0 and V0 with concentrated randomized or concentrated significant associations. If we look at this matrix version, the left plot is corresponding to the input matrix of this association between exposures and metabolites. So these red dots can be significant associations or high associations according to binarize this weight matrix W. Then we tend to identify this U0 and this V0 with concentrated significant associations. The reason why we are interested in such structure is based on graph combinatorics, the probability that a set of exposures are highly correlated with a set of metabolites converges to 0 under the norm, which means if the true significant edges appear according to Bernoulli distribution, then these red dots or these significant edges will randomly distributed in this whole graph. Then the probability to observe this parsimonious subgraph will have will converge to 0. And this lemma tells that this probability decays exponentially according to the increase of the subgraph size and the density of these significant edges. So in practice, if we could really detect such a subgraph with non-trivial size and relatively high edge density, it is highly to be true. To detect such a systematic pattern or this parsimonious subgraph, we propose this objective function. This objective function is equivalent to the edge density times the size of the subgraph to the power of 1 minus lambda. So we are maximizing the edge density and the subgraph size simultaneously. Then for each tuning parameter lambda, we could get the output of the subgraph by maximizing this objective function. And to determine this tuning parameter or determine the penalty of the subgraph size, we are using the likelihood function. So we consider the edges within the subgraph follow Bernoulli with pi1 and outside follow Bernoulli pi0. And we assume pi1 is higher than pi0. Then we use this mixture of Bernoulli likelihoods. We finally choose the tuning parameter and the associated subgraph to maximize this likelihood function. Here's the algorithm for maximizing the objective function. I'm just skip the detail, but the main idea is we are removing one node at each iteration and according to the aspect ratio to determine which set we are removing the node. For the real example, we are using the numerical exposure variables and on-metabolite variables. For this association matrix, we are using the pairwise correlation coefficients, but other metrics can also be used, like negative log p-values of regression coefficient or partial correlations accounting for confounders. So actually, binary or categorical variables can also be included in our study. And based on this input data, we are detecting a set of exposures and a set of metabolites, which has parsimonious multi-to-multi associations. If we zoom this subgraph, we will get this plot, and we can see there are mainly two groups of exposures and two groups of metabolites. The first group of exposures include mainly the variables related with air, some variables for meteorological and net spaces, and some other variables. And this group of exposures are slightly negatively associated with glycerophospholipids, while positively associated with amino acids and some other variables. The second group of exposures include about mantles, PCBs, and PFAs, and they have contradict directions of associations with metabolite groups. This top triangle is from the correlation between these exposures, and this right triangle is for the correlation matrix between these metabolites. And we can see the first group of metabolites of this group of glycerophospholipids are highly correlated with each other, and also they have similar association patterns across exposure variables. The second group of metabolites, although they are not highly correlated, but they still have similar association patterns across these exposure variables. Here's a zoomed figure. These variable names might still too tiny, but I have a full list of variable names in my GitHub files, so you could have a look if you are interested. To evaluate the performance of our method, we are using linear regression models. So we are fitting two types of models. For the full models, we are using the metabolites selected in the subgraph as outcome and all exposures as predictors. While in the reduced models, the outcomes are the same, but we only use the exposures selected in the subgraph. Then for the full model, we have 169 predictors, while for the reduced models, we have 92 predictors. And we are using R-squared to evaluate the variance explained by predictors. And we can see for the reduced models, we used about 55% of predictors, while we can explain more than 80% of variances comparing to the full model. Because this R-squared is actually increasing for models with more predictors, so we also use cross-validation to evaluate the performance. We are using 5-fold cross-validation. So at each iteration, we are using 4 folds or 80% of data as training to fit the model or estimate beta hat. Then we are using the left fold or 20% of data as testing data to predict y hat using these beta hats estimated from the trace set. Then we calculate this R-squared, this root mean squared error, and these the mean absolute error based on the y hat and the true metabolite values. And from the result, we can see the reduced models have higher values of R-squared and smaller values of these mean squared errors and mean absolute errors. So based on our comparison, we can see the exposures within the subgraph can better explain the metabolites within the subgraph comparing to the full set of exposures. And to summarize, in this project, we are focusing on identification of systematic associations between exposures and the metabolites. And this can also be generalized to other multi-omics data. And we are focusing on the parsimonious multi-to-multi association pattern detection. And we are using a computationally efficient algorithm. And based on our evaluation of the performance in regression models, we can conclude that the exposures within the detect subgraph have better explanation for the selected metabolites comparing to the whole set of exposures. Here are the files I uploaded in the GitHub website. That's it. Thank you for your time.
Okay, thank you very much, Kim, for your nice presentation. Is there any question from the audience? I don't see anyone in the chat. Xavier has one. When selecting the exposures, can you adjust for other variables? Yeah.
Yes, actually, for this association matrix, we can use some regression coefficient, pairwise regression coefficients to adjust for accounting to account for confounders. Yeah.
Léa is saying that there is a great visualization. I also agree with that comment. You can see very well how the variables are clustering, so this is nice.
Yeah.
I have a couple of questions. One is, how do you consider significant association paths? Just based on the p-value, do you correct for multiple comparisons or just fix a threshold? Which is the criteria for declaring that a path is significant?
Actually, if you want to evaluate the significance of this bicluster at the bicluster level, you could still use a permutation test to get the p-value for the cluster level significance.
Okay. And another question about, from practical point of view, I see you have selected metabolome, I suppose because this is a not so high dimensional data set, because I assume that the estimating processes can be very time consuming, isn't it?
For this data set, it's totally fine. Actually, the gradient algorithm is quite efficient in computation, and we also applied such method in even more in higher dimension data, and it's totally fine.
Yes. So, for example, for transcriptome, having 20,000 features.
Yes, we actually applied such algorithm in imaging genetics data, so it's almost 1,000 or 10,000 times 10,000. Yeah.
Fine.
Yeah.
And just to finish, one recommendation. I've seen that you have removed those variables that are not numerical. I mean, that are not continuous. But this is important for the exposome data because there are many exposures that can be measured as a not as a continuous variable. So maybe you have an idea how to extend your methods for dealing with categorical variables.
Yes, because actually I want to show these correlation matrices between exposures and metabolites. So I only use numerical variables. But actually in the first step, you can use, for example, the negative log p-values from logistic regression to include these binary or categorical variables.
Okay, thank you.
Thank you.
So is there any other question? No? So thank you very much for your presentation, Kim.
Thank you.
So let's move. There is a question pointed out, did you consider any confounders? I guess Xavier already asked this and the answer is yes. So Kion said that she was able to manage the confounders. So the next speaker is Jaime Benavides from Columbia University. He's going to present the talk entitled Pre- and Postnatal Urban Exposure Patterns and Childhood Neurobehavior. So Jaime, you can start whenever you want.
see the presentation?
Yes, we can see it, but we cannot hear you very well. Just try again.
No, you cannot hear me well?
It's very noisy. Even worse.
Sorry. Okay, now it's the same problem.
Yes, we can't hear you, but with making a big effort, and I don't know.
Yeah, let me get the auriculares 1 second.
Let's wait 1 minute. If Jaime kind of fix the problem, we'll move to the next speaker. So please, Nikos, be prepared just in case.
Better now?
Yes, I think so.
Okay, sorry for the delay.
No problem, that's fine.
Yeah. Okay, so I'm going to share my screen. Yeah, so our presentation is titled Pre- and Postnatal Urban Exposure Patterns and Childhood Neurobehavior. I've been working at Marianthis Chemorthoglous lab with my colleagues Janelli and Lawrence, and Janelli has been working on the health models, Lawrence in the pattern recognition analysis. I will first introduce our research question. So several studies reported detrimental neurobehavioral effects of urban air pollution in children and protective effects of access to green space. However, the influence of the urban exposome on children's neurobehavior remains largely unexplored. So we ask ourselves, are there any consistent pre- and postnatal patterns in the urban exposome data? And are these identified patterns, if any, associated with adverse neurobehavior in children? So now I'm going to introduce our methodological framework. So from left to right, we have been working with the urban exposome data, only continuous variables. So information like access to green spaces, meteorology, etc. And just to clarify, we didn't work with the omic or biomarkers data in this analysis. For the exposure patterns, we applied the principal component pursuit, PCP, which is a dimensionality reduction and pattern recognition algorithm from computer vision. And we coupled it with factor analysis to get the consistent exposure patterns. So the product, these exposure patterns and the unique or extreme exposure events were then combined with the potential confounders in the health models to examine the associations with the outcome, the children neurobehavior. So this principal component pursuit, PCP, is the innovation in this work, and it performs well in computer vision applications like video surveillance. For example, as you can see in these video frames, it takes the original frame and it decomposes it in a low rank matrix, which captures the background, and an sparse matrix, which capture the sparse events, which are important for the scene. In our case, with the urban exposures, the low rank matrix can be used to identify consistent exposure patterns, and the sparse matrix isolates unique exposure events. So the main advantage of using PCP as a pre-processing before running factor analysis or PCA is that it's not influenced by outlying values, and it can still recover the low rank matrix even in presence of missingness in the data. In addition, PCP has default penalization parameters that are theoretically guaranteed that can be used to get like the optimal solution using cross-validation And it gives you a number of ranks that you can then plug into the factor analysis as the number of patterns to be recognized. For the health models, we evaluated the association between PCP-identified patterns, so both the factors of the prenatal and postnatal together and children neurobehavior, adjusting for potential confounders. We first ran a generalized linear model with the quasi-Poisson for the count outcome data, and using as exposures of interest the factors, so the identified patterns. We then ran a generalized additive model to assess the non-linearity using penalization splines in the factors. For the unique exposures, so these extreme exposure events that don't fall within the patterns, we ran a LASSO model fixing both for the potential confounders and the factors to be always included in the model. The outcome is the CBCL total problem score, so higher values, higher neurobehavioral problems, and we adjusted for these potential confounders. So we're starting by applying PCP on the raw urban exposome data, and we get this kind of result. So here in this image, we have the postnatal low rank matrix. In the columns, we have the exposure families like air pollution, urban environment, indoor air pollution, etc. And then in the rows, we have the individuals organized by cohort. As you can see, there is a clear distinction between cohorts. So for example, cohort 3 has like very marked urban characteristics like high air pollution, high urban environmental variables. So basically we were able to recognize the cohorts, so the cohort patterns in the data, but we wanted to go beyond that, find inherent patterns in the data. So we decided to regress on cohort each of the urban exposures and to work since then with the residuals that we then ran PCP again. We got this new low rank matrix and we plug it into the factor analysis. We got for both prenatal and postnatal, the optimal solution of PCP gave us 4 ranks. So we estimated 4 patterns in the factor analysis in both cases. So starting with the prenatal patterns, so these are the loadings of the factor analysis on the prenatal low rank matrix. We obtained 4 factors: traffic, urbanicity, meteorology, and water pollution. So for example, thinking that loadings are like correlations for the traffic factor, we have air pollution in red, in blue we have noise, and in purple traffic. So all of them are positively correlated with the traffic factor. In the case of the postnatal patterns, so the loadings of the factor analysis for the postnatal low rank matrix, again, we have a traffic factor and an urbanicity factor, but interestingly, this time we were able to distinguish between the school environment and the home environment in the second and fourth factor. And we had another factor for meteorology. So we wanted to assess the association of these factors with children neurobehavior. We ran the generalized linear model, adjusting for the potential confounders. And here we have in the y-axis the factors and in the x-axis the coefficients. So in general, we got mostly a protective association. So for example, starting from the bottom, the traffic postnatal factor was protective, and in the middle, the traffic prenatal factor too. We were not expecting these results, so we ran single exposure models for example, for PM2.5 and NO2, and we got still protective associations. In contrast, for the urbanicity, school, postnatal factor, we got this detrimental effect on children neurobehavior. Then we ran the GAM model to assess the nonlinearity, and all the associations remain linear. So now these unique or extreme exposure events that don't fall within the patterns in the data, we have here a couple of examples. Yeah. Yeah, finishing. Thank you. So on the left, we have the prenatal traffic noise, on the right, indoor benzene, and these are the trends across individuals for the colored cohort. And you can see the big differences between the patterns and the sparse events, like for example, in cohort 6, in indoor benzene, in purple. So we ran a LASSO model to consider the associations of these sparse events with children neurobehavior, because in that information, there might be data useful to be considered when we are associating the exposome with the children neurobehavior. And running LASSO, which minimizes the prediction error by keeping only the variables that are more relevant to the outcome, shrinking some of the coefficients to 0, we got these results. So for all the exposures in the sparse events, we have these different coefficients, most of them 0, and we have these detrimental effects. So the highest is for benzene indoor air pollution, and then harmful to for traffic, prenatal traffic noise, and the postnatal traffic load. There were some protective associations, facility density in both prenatal and postnatal, and walkability in prenatal. And now, ending with the discussion and conclusions, we estimated the protective effect of traffic patterns on children neurobehavior, and similar results for single exposure models unexpectedly. And these unique or extreme exposure events that are not explained by the identified patterns, like traffic-related exposures or indoor air pollution concentrations, were associated with detrimental effects on children neurobehavior. In conclusion, using PCP combined with factor analysis, we identified consistent and interpretable pre- and postnatal exposure patterns, and it's an ongoing work to make this code accessible to a wider community and apply to new data sets. And for the unique exposures, we applied LASSO. We are now exploring interpretable and robust ways to include these results in health models. I want to acknowledge our collaborators and the funding. Thank you very much. Please ask me any questions. And if possible, I would like Lawrence, who has been working in the pattern recognition analysis, to join for the question and discussion. Thank you.
Okay, thank you very much, Jaime. Well, the first question here pointed out by Wiley is the same I had, which is, what's the difference between PCP and PCA? I saw your slide, but can you elaborate on that, which is from a practical point of view, which is the difference?
Yeah, Lawrence, do you want to answer that one?
Sure. Yeah, thanks for having me. And thanks for the presentation, Jaime. And yeah, it's a great question. PCP is originally a computer vision algorithm. It's a convex optimization problem with an objective function that penalizes the low rank matrix that encodes consistent patterns with a nuclear norm, and the sparse matrix encoding unique events with an L1 penalty, and then a noise matrix with a Frobenius penalty. The PCP algorithm that we adapted for this data is a non-convex adaptation of that with a best rank R approximation of the low rank matrix, and then the same L1 penalty on the sparse term, and the Frobenius penalty on the noise term. So it's an iterative algorithm that optimizes according to that objective function, while PCA, as depending on your background, is an SVD that can extract patterns. So the PCP is really a pre-processing step to get a low rank structure in the data before passing it on to a pattern recognition algorithm such as PCA or factor analysis. I hope that helps.
Is somehow considering possible sparsity with regard that some exposures in that case are not having importance? I mean, they are zero with regard to the loadings or something similar, or not? It doesn't consider
Sorry.
that.
Can you repeat that?
Yes, because in the PCA you have the loadings, you have with each factor, and maybe one variable is not important for that. So is the PCP just reducing to zero, to zero, that coefficient?
Yeah, so depending on the input rank for the non-convex program, you specify the rank for the low rank matrix. And so the optimization objective function will find the best rank approximation of that. So for all those patterns that fall outside of that rank, for example, if you ask for a rank 4 low rank matrix, and the full rank matrix could be rank 26, then ranks 5 through 26 won't be included and won't explain the variance in the ground truth low rank matrix.
Okay. Is this method able to consider supervised approach? I mean, because you run first PCP and then assess the association between neurological outcomes. Is possible to put all together?
Yes, definitely.
Okay.
Yeah, we're exploring that in ongoing future work. But just like you can have supervised PCA, you can have supervised PCP.
Okay, thank you. Is there any other question? I guess, Jaime, the findings you obtained, they are, I mean, at least they are reproducing what we expect. There are different cohorts having different exposure patterns. You ended up with the most important ones regarding to the mainly environmental, green spaces, and so on. And maybe you could share your result with our colleagues, just because we did similar analysis, and maybe you can share the result you obtained. And also for the neurological outcomes, I don't know whether you saw the paper that Martine has showed in the presentation about linking exposome with the neurological outcomes. It's a paper that is already published or is in press. I don't know whether you know the paper.
Yeah, I don't know specifically that paper, but yeah, please share it with us, and we are very happy to continue the conversation. And yeah, I just kind of landed to the group some months ago, and I was able to do all this part like as a user perspective to learn, collaborating with the team, developing all these methods. Yeah, it's quite like friendly and approachable. Yeah, we really want to apply to new data sets and to collaborate on that and make it more robust.
Yeah, because your approach was different, because your approach was multivariate and the other one was univariate, analyzing one by one, and maybe your approach is having more power. So thank you.
Thank you.
Okay, so if there are no more questions, just Léa just put the link for the green space with these controversial findings you saw. Okay, so let's move to the next talk, which is given by Nikos. The title of the talk is he's working at the University of Southern California. The title is Latent Unknown Cluster Integrating Multi-omics Data, Lucid, with phenotypic traits. So go ahead when you want.
Thank you, Juan Ramon. And it is often said that epidemiologists are playing in the backyard of statisticians when doing analysis. So I'm an epidemiologist in training, and the Lucid method is the backyard of Yin-Chi Yao, a talented statistician and PhD student from our department. So I think that Yin-Chi is the most appropriate person to talk about this method. So I will pass the floor to him.
Yeah.
Thank you.
Yeah. Thanks, Nikos. Thanks for the brief introduction. And it's always a pleasure working with you.
So maybe I can share my screen to start the presentation. Okay, can you see my screen?
Yes, perfect.
Okay, cool. So today, the topic that I will introduce is a novel statistical model that integrates multi-omics data. And this model is called Lucid and is currently the statistical method that I'm working on. So let's start. The research question that we want to address specific to this data challenge is whether early life exposure to organochlorine increase obesity risk. And if the answer is yes, what are the underlying mechanistic pathways behind the same? So a little bit about the history. Back in 2002, physician Paula Bailey-Hamilton conducted a study suggesting that obesity epidemic correlated with the increased production of synthetic chemicals. So among them, organochlorines, or OC for short, constitute a major class of synthetic chemicals. The effects of OC are biomagnified through the food chain and especially affect the health outcome of pregnant women and children. So here we measure the BMI as a continuous Z-score, and driven by the research question, we can conduct a conventional analysis that is build a multivariate linear regression model and examine the association between BMI and each exposure. However, that left one question unanswered. What is the underlying biological process between the exposure and the outcome? So we extend the conceptual model based on some biological knowledge. Here we assume the OC will influence the BMI through some biological pathways, and children with different BMI will have different biological pathways characterized by various expression level of some proteomics or metabolites. So here we will refer these proteomics and metabolites as omics profile. Since every biological pathway can be treated as a factor, then this model is equivalent to estimating the subgroups in our data. We will formalize our conceptual model into a statistical framework called Lucid. So this model was initialized by my mentor, Professor David County from University of Southern California. So here, the three components we are considering: the exposure profiles to OC, the proteomics, urine metabolites and serum metabolites, and the outcome BMI are all connected through a latent unobserved variable, X. So this X is a categorical variable, and each category is interpreted as a subgroup in our data. So a little bit more about the details of statistical modeling. The association between exposure and the latent subgroup is modeled by a softmax function, and conditioning on X, the omics profile is described by a multivariate Gaussian distribution. And additionally, still conditioning on X, the outcome Y, the BMI Z-score, is modeled as a normally distributed variable. So here, because X is unobserved, we implement an EM algorithm to estimate the model parameters of Lucid. And this is the expected likelihood we're trying to maximize by this EM algorithm. So back to our data challenge. Now we will reframe our research question in terms of Lucid model. Specifically, the question we want to address is, first, identify the subgroups with high BMI Z-score. In other words, we're trying to identify the subgroup associated with obesity. And secondly, discover the subgroups by distinguished omics profile. And lastly, estimate the association between exposure and subgroups. So in order to decrease the noises in our data, we first conduct some preliminary screening on metabolites. Specifically, we examine the variable, the association of each variable in the omics profile and to the exposure and to the outcome. After adjusting for multiple comparison based on false discovery rate, we picked up 45 variables in the omics profile that are significantly associated with both exposure and the outcome. However, that is still quite a lot in terms of interpreting the Lucid model.
So we additionally conduct an integrated variable selection based on Lucid. So this method utilizes a combination of LASSO penalty and a graphic LASSO penalty, which regularize both the mean and the correlation structure of our omics profile. So our final Lucid model will contain 14 omics signatures. Now we will jump to the results of our analysis. Oh, and one thing to mention, when fitting Lucid model, we need to specify the number of subgroups. So here we did a grid search on K, which is the number of latent subgroup, and use BIC, the Bayesian information criteria, as our model selection criteria. The up model contains 4 subgroups. So this is the plot that presents the association between each subgroup to the BMI Z-score. The number in the parentheses represents the number of observations assigned to each category based on the predicted probability of Lucid. So we can see that there is an increasing trend from subgroup 1 to subgroup 4 in terms of BMI Z-score. And subgroup 4 that has an average BMI Z-score equals to 2 is the high risk of obesity group. So our further analysis will focus on this subgroup. So next, we will present the unique omics profiles for each identified subgroup. So this figure, the y-axis, represents the estimated mean value for each omics signature in our data set. And we can observe that every subgroup has their unique distinguished omics profile. We want to specifically highlight the proteins in the blue box. So subgroup 4, the high-risk subgroup, is particularly characterized by the RL1 beta, RL6. These two are the key biomarkers of inflammation in the human body. And also, subgroup 4 is characterized by the high level of insulin, which is widely known as a factor associated with obesity and the underlying metabolic dysfunction. And lastly, we want to present the association between the exposure profiles and the identified subgroups. So here, the y-axis represents the log odds ratio, and we use the subgroup 1 as our reference subgroup. So as you can see, the exposure profile characterization is mainly driven by the variables in the blue box, which is the HCB exposure in mother and children. So specifically, if we're moving from the subgroup 2 to subgroup 4, the concentration of childhood HCB are decreasing, while the concentration of maternal HCB are increasing. And if we recall that subgroup 4 is associated with high risk of obesity, so that means maternal HCB is positively correlated with obesity, and HCB in children is negatively correlated. All these two opposite directions are proved by previous literature. So lastly, because Lucid is an integrated model to combine all these information, we also provide a visualization tool based on Sankey diagram. So here is the Sankey diagram. Every node in this diagram represents a variable in our data, and every edge represents an association. So specifically, the width of the edge represents the effective size of the association, and the color represents the direction. If it's a light gray, it will be a negative association. If it's dark gray, it will be a positive one. So specifically, this Sankey diagram illustrates the association between the subgroup to the outcome of interest, which is BMI Z-score, the latent subgroup to the metabolites, and the association between the exposure to the latent subgroup. At first glance, this Sankey diagram might look a little bit overwhelming. However, there's an interesting pattern can be observed, and you can easily map these edges or the associations back to our previous omics profile and exposure profiles. But due to time limit, I won't introduce that part into details. So to sum up, for this data challenge, we implement Lucid, a novel statistical method for integrated multi-omics analysis. And we identified 4 latent subgroups characterized by distinguished exposure profiles and omics profiles. And we also examined their association to the obesity. We confirmed the previous HELIX publication results that childhood HCB exposure associates with reduced childhood BMI Z-score. And then we also confirmed the previous literature that prenatal HCB exposure increases BMI. So additionally, by using the multi-omics profiling, we identified the signatures, including IL-1 beta, IL-6, and insulin, that gave insights into the underlying mechanistic pathways behind the scene. And that's all my presentation. And a special thanks to Professor David County and Dr. Nicholas Strategies for their invaluable suggestions to this project. So all codes are uploaded in this GitHub account, and an updated version could be found by the latest branch of this GitHub account. A previous version can be found on Icahn, which you can directly download. And that's all my presentation. Thank you. And if anyone has any questions.
Okay, thank you very much, Inky, for the nice presentation. I don't see any question in the chat. Is there anyone having a comment, question? Okay, I have a couple. One of the question was addressed in the presentation because you mentioned that you are using the EM algorithm. And so I was wondering or worried about how to estimate the variance of the parameters just to provide the p-values. And I saw that you use Bootstrap. So this makes even more computationally demanding the algorithm because the EM algorithm is slow. Doing bootstrapping is even slower. So how do you think that this method will scale to analyzing the methylome or the transcriptome, which is having 20,000?
Right. Actually, that is a computational problem and also a technical issue related to EM algorithm. So if we go back to the details of Lucid, so here in slide 6, so in the EM algorithm, at each iteration, we need to calculate the probability for observation I assigned to cluster J, given the current data and estimate. And because when we calculate this probability, we need to use the density function of the multivariate exposure, multivariate omics profiles. And for methylation data, which contains of thousands or 10,000s of variables, on this value, multivariate Gaussian distribution is extremely small and couldn't be stored in terms of our 64-bit machine. So we suggest when we dealing with such high dimensional data, we first conduct a preliminary screening based on the association between the exposure and the outcome, and then limit the number of variables entering to Lucid. So here for our analysis, we're just trying to limit the number into 40 to 50. And in practice, we're trying to, we suggest to limit that number below 200.
200.
Yes.
Okay. So another question is, did you perform any sensitivity analysis just changing the number of clusters instead of using 4, maybe 3, because the second cluster is having only 37 individuals, and maybe you collapse the first and the second. By having a look at the box plot, it seems to be pretty similar with regard to the set BMI.
Right, that's a very good question. I haven't conducted sensitivity analysis because usually we believe the Bayesian information criteria is, in practice, the optimal standard to choose different K. And usually, if we collapse 2 subgroups together, that will change the whole structure of Lucid, and the whole model parameters might be, not statistically significant anymore. So we basically just use the Bayesian information criteria.
Okay.
But yeah, that's a very good point. And I think in the further development, I should incorporate, sensitivity analysis for the clustering and compare the results of that to the Bayesian information criteria.
Okay. So there is a question in the chat. What about data with multiple time points for the omics data? I guess this is a complicated question.
Yeah, that's a very complicated question. The question is for multi-time point omics profile or the multi-time point outcome.
Yeah. Multi-time omics, so it's even more complicated.
Okay.
Maybe we can leave this for the final discussion, because I guess it's an interesting point. And finally,
okay,
just to finish, Sinhi is asking, what does the latent variable X represents? I think this is an important question just to understand the method.
Yes, right. So here the latent variable X represents the number of subgroups in our data. That, it is a technique of dimensional reduction. So for example, if we have a cluster of data and we're trying to find some patterns in this data, and we're just trying to kind of, clustering the data into different subgroups, and these subgroups could be summarized by using just a few parameters. And that is the meaning of X statistically. Or in terms of biological terminology, you can regard these X as a biological pathway. How many different biological pathways in our data that could associate the exposure to the outcome.
Okay. Okay, so thank you very much. Okay. Let's move to the last speaker.
Thank you.
Thank you. CU1 from National Institute of Environmental Health Sciences is going to talk about integrative analysis and visualization of the exposome and transcriptome data. So this is nice to see that transcriptome appears. So this is the only one skipping metabolomics and proteomics, which are very moderated tables. And this is a very important aspect dealing with large data sets. So please, when you want, you can start.
Yeah. Can you see my slides?
Yes, we can see it.
Yeah. Okay. Yeah, so first, thank you so much for introducing me, and I'm the last presenter, and I hope I can make a good ending for our today's workshop. So this work was done by me, Vrijheid, and Glen, and we are from EHS, and we focus on building an integrative framework of exposome and transcriptome to study the mechanism of asthma. And here are some background and the motivations of our work. So in the past years, more and more studies have shown that the development of human disease involve a highly dynamic and interactive system of molecular layers. For example, genetics, epigenetics, mRNA transcripts, proteins, and metabolites, and are influenced by many environmental factors. And our group are interested in studying asthma, which remains an important public health problem in the United States, as well as worldwide, because of its high morbidity and inadequate disease control. And there was a recent study by researchers from University of Toronto. They have found a strong evidence that environmental exposures affected gene expressions associated with asthma much more than genetic ancestry. Since assessing the effect of various exposures on gene expression might be useful to generate hypotheses about potential cellular mechanisms through which exposures may influence the development of asthma in the human population, we applied our proposed framework of integrating exposome with transcriptome on the asthma outcome. And here is an overview of our integrative analysis pipeline for identifying the causality of exposures on asthma by perturbing gene expression levels. And there are 3 different modules in the pipeline. First, we will apply differentially expressed gene analysis and gene set enrichment analysis to discover gene expression profiles and their function roles associated with asthma. And in the second module, we did a variable selection and defined an environmental risk score of all selected exposures and for each exposure family. And this step aims to reduce the dimension of asthma-associated exposures and obtain the group effect of each family. And finally, we joint model the exposome and gene expression data processed from the previous two modules using the framework of high-dimensional mediation analysis. We estimated the mediation effect of gene expression for single exposure as well as for family-based environmental risk score. And I will go into each module for more details. Now look at the results from module 1. By applying the Lima package, we identified more than 800 DE genes associated with asthma after adjusting for 3 covariates. And in addition, the gene set enrichment analysis were applied as well to understanding those genes' functionality. And for each analysis, several figures would be generated for visualization, such as the volcano plot for DE genes and the dot plot for enriched pathway, as I showed here. And due to the time limit, I will not present the details of the gene expression profiles. But if you are interested in those results, we have put our code on the GitHub for the references. Another major step before integrating with gene expression dataset is to reduce the dimension of exposures. So by exploring the whole exposome dataset, there are some clear correlation pattern among both intra-family and inter-family exposures. Thus, we first use elastic net to do a variable selection, since it can deal with correlated relationship across exposure variables by a combination of ridge and lasso penalty. And we have picked 6 covariate variables as confounders. And as shown in this summary table, although age, birth weight, BMI of child, and ethnicity are not significantly associated with asthma in this data set, several previous studies have provided evidence for treating them as confounding factors. And finally, 76 exposures in 17 various families were selected as asthma-associated exposures. And here we present the effect size of those 76 exposures, where many well-known asthma-associated factors, such as different pollutants, metals, and smoking status, were chosen in our model. And we further reduce the dimension of pre-selected exposures by calculating the environmental risk score for each family. Here, the ERS, family-based ERS, is defined as a linear combination using the coefficient produced from the elastic net applied across each individual's observed exposure measurement in the corresponding family. And by looking at this association between the 17 family-based ERS with asthma, we identified that most of the exposure families whose effects are well known for influencing the asthma, such as air pollution, built environment, metals, and smoking, are significant. Besides, combining exposures into family-based ERS is beneficial to reduce the collinearity across intra-family exposures. As displayed in this correlation heat map, we could see the absolute correlation among ERS is ranging from almost 0 to 0.57. In addition, a total risk score is calculated as well by using all 76 pre-selected exposure. And we divided those total risk score into 10 equal sets group according to its quantile value. Then by looking at this histogram, people with a higher total risk score tend to have a higher chance with asthma. Therefore, total risk score could be a good index for predicting asthma status. Finally, we integrate the gene expression and the exposures by a high-dimensional mediation analysis. We are considering all mediators simultaneously and adjusting for covariates. And in the first model setting, we build a single mediation model for each individual exposure. That is, the independent variable X here is a single exposure selected from the elastic net, while MK are all the potential mediators, which are the genes identified before. And C are all covariates, and Y is our outcome asthma. And then we examined whether there was a significant mediation effect, alpha times beta, by the path of exposure to gene expression to asthma, while accounting for covariates. And this table lists 33 exposures reveal at least one significant mediation signals while controlling the FDR at 0.1. And in our second model setting, we build a single mediation model for each family-based ERS. That is, the independent variable X here is replaced by ERS for an exposure family, and all other settings remain the same as the previous model. At the end, we observed 7 exposure families were significantly linked to mediator genes, especially for air pollution and traffic. The mediation effect was chiefly driven by gene CES1. And for social and economic capital, the effect was driven by gene NEO1. And these are very encouraging results, as I will show in my next few slides. And it is also interesting to notice that all the mediator genes identified for ERS effect remain the same relationship for single exposure identified in model 1 by comparing those two mediation model settings. And we also did a literature research to see whether there were existing publications to provide the biological evidence to support our finding. And indeed, several previous studies have shown that the separately association of air pollution or traffic, gene CES1 or NEO1 with asthma. Although these have been shown to be independently associated with asthma, our mediation analysis results suggested that gene CES1 gene is a mediator, which hypothesizes a potential pathway or cellular mechanism where which air pollution or traffic could affect the asthma phenotype. And this connects with our original aim for integrating exposome and gene expression data. And there were also existing studies supporting the association of other exposure families observed in our model with asthma. However, we explored 3 novel genes as their mediators: VESP41, SNORA10, and ZNF786. However, none of their relationship with asthma have been verified before. Thus, further studies might be needed to explain the mechanism by which of the above families influence the asthma phenotype, where the novel mediators identified in our mediation model. And here is a summary of our proposed framework. So one of the major strengths is that we relied on high-dimensional mediation analysis algorithm for which multiple mediators could be modeled simultaneously. Another is that we calculate the environmental risk score for reducing the exposure dimensionality and extract the cumulative effect of multiple exposures in the same family. For model extension, we are working on developing a novel method by taking consideration of gene clusters to model the mediation effect due to the interaction and dependence among genes in a known biological pathway. And this would help to further reduce the mediator dimension and boost power and accuracy in estimating the mediation effect. And one of the limitations of our work is that we only consider 2 omics data, exposome and transcriptome. Recall that any human disease is relied on the effect of multi-omics interaction and the environmental exposures. Therefore, incorporating more omics, such as DNA methylation and metabolome, and their interaction with the transcriptome could further explain the etiology of asthma. And thank you for all the help from my research group. Yeah, and I'm happy to take any questions.
Okay, thank you very much to you for the nice presentation. There is a question in the chat. I don't know whether Vivian has already answered, but maybe you can comment on that. Is how does collinearity among different exposures differ from interaction among different exposures? Vivian has already answered.
So the collinearity between different exposures differ from interaction among different exposures. Do you mean that question? Sorry, yeah. Actually, I don't have a good answer to this question because here, when I talk about collinearity, we calculate the correlation between exposures. But for interaction among different exposures, I think that are relied on like some biological mechanism between exposures. So
yes, I'm sorry, maybe this question was for a previous presentation, so
okay,
maybe, but it's fine. You addressed it.
Yeah.
I don't see any question. I have one. I'm very surprised about this environmental risk score. Is this something from you? Is just published in any paper? Or is that idea already published?
No, we didn't publish any papers based on this idea. Yeah,
have you read this term, environmental risk score, anywhere? Or is just something you have invented?
I think this idea is from the GWAS analysis.
Yes,
so,
I know,
yeah,
because
yeah.
risk score, but I haven't heard anything about the environmental, just summing the effects. Because I have a question related to that. How do you consider that maybe some Nikos is saying that there is an edge methods using such a score. Okay, thank you, Nikos. The question is how they consider that some couple of exposures can be correlated. So if one is significant, another one will be, and you are increasing. Okay,
yes.
Thank you, Nikos. Yes. Can you say something to you on that?
Yes, because by grouping those exposures into environmental risk score, we can identify the group effect. So I think it will improve the power to estimate, to get some like significant signals.
Okay. Are there other questions? Xavier has one question. Could you calculate the percentage of mediated effect?
Oh, yes, actually we have the percentage of the mediation effect. It's not very big, but that's one possible reason is that because we put all 800 DE genes into that mediator models, but we are now working on try to calculate the joint effect of all the mediator effect. But the percentage for our findings is about 5%.
Okay. So in the chat, there are still people discussing about one of the lucid
the ERS
presentation.
Yeah.
So that's what I was missed. So thank you to you. So now it's time for some discussion. We can have maybe 5 or 10 minutes and we finish because it has been a long presentation. So please, those who have presented something, please switch on your camera. And I will ask something. Well, first, I would like to thank you for all the presentation. Very, I learned a lot, and I saw new results and things. It's very, very nice to learn something when you attend this type of workshops. And I was surprised to don't see anything about multivariate methods for integrating multiple tables. I mean, there are many techniques such as canonical correlation, generalized canonical correlation, which is principal component analysis, but having more than 2 tables. And there are many methods for doing that. And do you know those methodologies? Do you have an idea about whether this can be better than the method you have provided? Because I guess your methods are more hypothesis driven. I mean, you should select one phenotype, one omic, one. Can anyone say something about those methodologies? Lawrence, do you know an extension of this PCP for more than 2 tables, or not for
No,
1 table, more than?
Yeah, at the moment we're just trying to get some clarity out of it for single matrices, single exposure matrices. It's very robust in computer vision, and so to adapt it to environmental health data or omics data has proven to be quite the challenge. And so we're still playing with that before we take it anywhere beyond there.
Gennings, do you know these methodologies that are putting everything together, 5 tables with thousands of features? How this compares with your approach?
Well, I haven't known too much about that approaches, but I think the key idea for this is dimensional reduction. And I think in terms of that, Lucid is also dimensional reduction. We're trying to summarize, different features into just a categorical variable and use that categorical variable to represent the whole integration of the data.
Okay. And another point, maybe we have another one and we finish, is about whether these methodologies can deal with missing individuals. I mean, you have been linking different omics or different also phenotypes, and maybe one individual can be missing from one omic data. So how do you analyze the data? Just complete cases? Do you know any approach for, let's say, not removing the information from one omic data? So is there an idea about that?
Oh, yeah. And actually, for the Lucid model, we have an extension for missing data, especially in the missing patterns in the omics profiles. We can incorporate complete missingness that the omics measurement is just absolutely missing for some of the individuals. And we can also incorporate the sporadic missing pattern that, some of the metabolites are missing in these individuals and some of the metabolites are missing in that individual. And the updated version of Lucid will be focused on that type of analysis to deal with missing data.
Okay, Lawrence, any comment?
Yeah, our implementation of PCP during our attempt to extend it to environmental health data and omics data is also able to handle missingness. We use information in rows that have observations more than or greater than the rank of the matrix as quote unquote safe rows that have enough information to infer the missingness in the data, and then rows that don't have enough observations at least equal to the rank of the matrix are quote unquote unsafe rows in which we use an imputation scheme instead of inferring the missingness. And in this way, we kind of have a hybrid approach. And that's been shown in simulations to recover missingness really, really well, better than just one or the other.
Okay, excellent. Is there any general question among the people who are attending this last presentation? No, maybe we can finish with one of the questions that has been raised during one of the presentation is about repeated omic data. I mean, longitudinal data is being available very soon, not only for the exposome, but also for the omics. You know that the dynamics is very important. For any of you, can anyone tell me how your approaches can extend for the case of having longitudinal either omic, genomic, transcriptomic, or exposome data?
Yeah, I think for Lucid, I already proposed some ideas in the chat, but I can illustrate that with more details. So here we currently have one latent variable that models a cross-sectional omics profiles. But in the future development, we're proposing that we can have a series of latent variables, and they are timely dependent with each other. And each latent variable could model and summarize some features of the omics data at each time point. So by that way, we can incorporate the longitudinal data analysis into the framework of Lucid. Yeah, that's my point.
Yes, very clever idea. Yes, seems to be working. Any other comment or question? Well, if not, I would like to just finish thanking all of you for making the effort of preparing the data, the analysis, the presentations, and just one comment. I'm in charge of putting all the code you have used in the GitHub. So as I mentioned in the chat, if you have a GitHub account, just send me the link where your code is written, and I can just put a folder with your name and just add the link, and maybe this is better to avoid extra work. Okay.
Yeah, thank you.
Yeah.
We have done this pull request, and I hope you can get
Yes,
it from there.
I will accept definitely. Okay.
Yeah, and thank you for organizing this great event. Like, yeah, it's been so exciting.
Thank you for the interest on presenting your analysis. It's very nice. Okay, so just finish this presentation, and tomorrow we'll see at the same time having more and more presentations. Léa, maybe you can say something to end the session.
Yes, thank you very much, and also to the chair, to Charline and Juan. I think you've animated like very nice general discussion after each presentation. Tomorrow we're starting again at 2:30 with a talk from Mark Shadow from Imperial College. He will present things about more like network analysis and maybe scores, I'm not sure. He will. So that's a keynote for 30 minutes, and then we'll have other talks about omics and machine learning. So thank you very much to everyone, and we will have a recorded session, the video, and also the slides and the code will be available on the event website. Thank you very much to everyone.